Okay, hey, welcome to a series of videos on organic chemistry. This course is an introduction to organic chemistry, and it's going to go over the basics you need for a first year organic chemistry courses in most curriculum, but this is specifically targeted for NCEA. Okay, so what is organic chemistry? Well, organic chemistry is the study of complex carbon compounds, except for carbon oxides and carbon carbonates. Organic compounds are commonly found in all living things. That's where the word organic comes from living organisms. But it's also found in fuels like oil, coal, and gas, because those are all made from once living things as well. And it's these types of fuels, especially oil and gas, are used for the precursors or the starting materials to make lots of organic compounds that we have in our everyday life. So the special thing about carbon is it readily bonds to itself. So a carbon atom will join to other carbon atoms, and it will do so in a big long chain and in complex structures, not necessarily a train, but a tree-like structure. Now this ability to do this is called catenation. It can also bond to a variety of different atoms, and that gives the different organic molecules the properties that they have. So it can bond to hydrogens, oxygens, sulfurs, carbons, nitrogens, chlorines, fluorines, etc. The other special thing about carbons, as well as being able to bond to all of those atoms, is they will form 4 bonds. So there are 4 different bonding spaces, and it can make double bonds and triple bonds with themselves or other elements. So it can form millions and millions of different types of complex compounds. So let's just have a look at a few of these complex compounds. So an example here is dopamine. Now dopamine is called dopamine because it has this amine group on the end of it. Now this is a neurotransmitter. It regulates mood, motivation, reward, and influences like, do you find pleasure in things, focus, movement. If you have imbalances in this or not enough of this, it can lead to disorders like Parkinson's or addiction. So dopamine is really critical for cognitive function, emotion, and well-being. And it's important that we sometimes need to be able to understand how this works, or maybe make this molecule or other molecules like it to help people who have problems with their disorders to do with either too much or not enough dopamine. Caffeine. Here's an example of caffeine. Now, just when we look at these molecules here, actually each one of those intersections of lines is where a carbon atom is. Now you can see that there is a very complex structure of carbon atoms and nitrogens and oxygens here. Now this is caffeine. Now caffeine is a stimulant found in coffee, tea, Coke, energy drinks, and it blocks andesine receptors. So it focuses, it enhances focus and may cause insomnia, because caffeine is widely consumed throughout the world and it affects the central nervous center. Now, if we know that caffeine can do that, can be used as a stimulant to make people more attentive, then maybe we could make a molecule similar to caffeine and it would have similar results. So that's why it might be important to understand how this chemistry works. Okay, what about adrenaline? So this is also called epinephrine. Okay, this is a hormone that triggers the fight or flight response. So if you've ever been shocked, someone surprised you, and you get that burst of sort of alertness, that's the adrenaline being pumped from your adrenal gland into your blood. Now it's released during stress. It increases your heart rate, your blood flow, your energy, and it prepares the body for rapid action, right? Now, interestingly, so if you compounds similar to adrenaline are put in EpiPens, so that when you have an allergic reaction that swells up your throat, you can take this fight or flight chemical, you can put an injection in there to increase your blood flow rate and energy and everything else to counteract the effect of your body to the, I guess, the effect of the swelling or your reaction to whatever it is you've been allergic to. So another chemical so these are all quite complex arrangements of carbons. But actually, all of these types of chemicals that either interact with our body or we use are really important, and there are thousands of types of them. And people who understand organic chemistry can understand how we might make these, change them, investigate them. Serotonin is the last one here. It's a neurotransmitter that stabilizes your mood, your sleep, your appetite, promotes happiness, calmness. If you have low serotonin levels, it can cause depression and anxiety. And it also regulates your digestion, and it can be influenced by diet and exercise. Now, if we know that someone has a low serotonin, then maybe we can give them something that is approximate to serotonin that will replace it, or we can give some serotonin, or we can try and identify problems by identifying the chemicals that are the reason for either there's too much or there's too less of them. And that's one important reason why we can do the study of organic chemistry, is so that we can unpack all of these types of chemicals that influence our world and our bodies. Okay, so in this video, we're going to look at the functional groups and how they might alter or change specific organic compounds. So here is a hydrocarbon, or a basic organic compound that's made up of carbon atoms joined to carbon atoms, with hydrogens filling all the extra bond spaces around the carbons. Now, in this molecule here, I've drawn carbon atoms with their selected bonds going to either the hydrogens or carbons. And in other places, what I've done is I've taken a carbon atom and I have condensed, or I've not shown all the bonds of the hydrogens, but I've just written hydrogen. So on the top at the left here, you can see here's a carbon showing the 3 hydrogens. On this bottom point here, here's the carbon, but I've just put H3. And if we ever see that, we assume that it is just this group here. Now this is an alkane, and this is called just a hydrocarbon because it is made up of just carbons and hydrogens. Now you can notice here that every carbon always forms 4 bonds, and actually every hydrogen just forms 1. So remember, on this carbon here, 1, 2, 3, 4 bonds. If we look at this condensed group at the bottom, this carbon has 3 bonds to 3 hydrogens, plus the bond that we can see to the carbon. It has 4 bonds as well. Anywhere that you see a carbon, it will have 4 bonds. And if you've ever drawn a molecule for an organic compound and the carbon doesn't have 4 bonds, you've made a mistake. Hydrogens always have 1 bond. Molecules that contain, just like I said, carbons and hydrogens are called hydrocarbons. Now, hydrocarbons in themselves have their own specific properties. They are insoluble in water. They can readily combust with oxygen to form carbon dioxide and water. But they usually don't have lots of specific organic properties in animals or plants or people. So what we can do is, if we take what is essentially a hydrocarbon and I replace a hydrogen or a CH3 or any part of it with a functional group, I can change the function or how this molecule works. Now here, there are 8 functional groups I've given, or if you assume that the 3 at the bottom are similar, 6 different functional groups. Now these functional groups are the common functional groups we have to be aware of in this introductory course, in this level 2 chemistry course. So we have carboxylic acids, alcohols, amines, alkenes, haloalkanes, which are chloroalkanes. We have bromoalkanes and fluoroalkanes. Now you can see here that I've drawn in the second column. You can see the second column here. Here is my carboxylic acid. It has a carbon with 2 bonds to an oxygen and an OH. An alcohol has a carbon that has an OH attached to it. An amine has an NH2. An alkene is a carbon-carbon double bond. An alkyne is a carbon-carbon triple bond. A haloalkane is this carbon joined to a halogen. Now, it's a chloroalkane if the halogen is chlorine. It's a bromoalkane if the halogen is a bromine, and a fluoroalkane if the halogen is a fluorine. So let's look at these molecules here. Can you identify the functional groups? Just take time and see if you can identify, using this table, the different functional groups that are in these different molecules that would change the original way that properties that they have, and they would work from the original hydrocarbon, but now we've swapped out functional groups. So if we look at this first molecule, we can see that there is a fluorine functional group, and that's the same as down the bottom. Here we can see the fluorine functional group, so this is a haloalkane. Okay, this molecule would now be classified as a haloalkane. The second molecule here, we can see that, or down the bottom here, we can see that it has a carbon double bond carbon functional group. So this is an alkene functional group. It also has another functional group in NH2, and this here is an amine functional group. If we go and look at this third molecule here, we can see it has an OH, and you can see here that an OH is an alcohol functional group. It has a chlorine. Here you can see a chlorine is a haloalkane functional group. Wait a sec. And we can see that there is a carboxylic acid group, the C double bond OOH, or sometimes just called COOH. So this molecule has 3 functional groups. Now in complex molecules, this is really quite common, but mostly when we do organic chemistry at this level, we'll just be looking at molecules that have 1 functional group, and as an exception, maybe 2. Okay, if we look at this last molecule, we can see there are 2 functional groups, this triple bond, carbon triple bond, which is an alkyne, and this haloalkane, another haloalkane functional group. So we have all of these different functional groups that we can identify in molecules. Now this is really important because the first skill that we're going to learn to do is identify functional groups and name molecules. I'm going to do that in the next part of the video. Right, let's look at naming organic compounds. So when we name organic compounds, we've got 3 things we're going to be looking at for a start. The first, we're going to look at how many carbons there are in the longest chain. This is called the parent chain, and we have what's called the parent name for that. We're also going to, at the bottom here, we have a table, and we use the table to find the prefix for the parent name. If there are 4 carbons in a chain, then the start of the name will be bute. Secondly, what we do is we look to see if there are any special groups or functional groups in the parent chain, and if there is, that will determine its suffix of the parent chain. So if there was a double bond carbon in the parent chain here, it would have a suffix of -ing. Okay, so and the last thing we need to look at is, are there any substituents or any groups or atoms that are coming off the chain, and we'll number those appropriately if we do. Let's have a look at a few examples. So the first one here is this molecule, and if we want to name this molecule for the parent name, we need both the prefix, the start, and the suffix, the end. So the first thing we note is there are 8 carbons in a row. So if we go to the top, table at the bottom, we can see that 8 has the associated prefix oct. So the start of this parent name is going to be oct. And because here the only type of bond that it has is a carbon-carbon bond, this one here, its suffix is going to be -ane. So this molecule is going to be called octane. We don't have any other functional groups coming off apart. There's no atoms attached apart from hydrogens, so this is its name in full. Let's look at the next molecule. Okay, so if we look at this molecule, what do you think its name is? How many carbons does it have? What's its prefix? And what is its suffix? So, of course, this has 2 carbons. Its prefix is eth, and it only has carbon-carbon bonds, so it is -ane. So its name is ethane. The next one. What do you think this name would be? Okay, 5 carbons. It's going to be pent, and it only has carbon-carbon bonds, so it's going to be pentane. And the last one we look at here, okay, this is a wee bit different, this one. We have a group here, a functional group coming off, and it's called a methyl group. Now, it's not going to change the name of the suffix. So if you look at the table on the right, there is no suffix associated with this. But the parent name is going to be 3 carbons in a row, which is prop, and it only has carbon-carbon bonds in the main chain here, so it's propane. But we also have to deal with this group coming off, and this is a methyl group. So this is going to be called propane as its parent name, but it's going to have its group coming off, its substituent called methyl propane. And that's how we name these introductory organic molecules, or the more simple ones. Okay, let's keep looking at organic compounds. So I've got 4 different ones here. Let's start with the one on the bottom left here. Now what we can see in the bottom left molecule is that we have 5 carbons in a row. So we know that this is going to be pent. It only has carbon-carbon bonds, so its name will be pentane. Have a look at the one on the top right. Now this is slightly different here. We still have some carbons in the parent chain. So we have 2 carbons, so its prefix for the parent is going to be eth, but we have this OH group here. And if we look in this table, we can see that OH here is called a hydroxy, but it has the suffix -anol. So this now is going to have this, the start of the name of the parent name is eth, but the end is -anol. So this is going to be called ethanol. Let's go to the next molecule. Well, the next molecule here only has 1 carbon, so it's going to have, but it also has this functional group, the chlorine off here, which is a chloro functional group. It doesn't change the suffix, this substituent or functional group. So it's 1 carbon long, it's called meth. It doesn't change the suffix, so it's only carbons and hydrogens, so we're going to call it methane. That's the parent name. But we need to also deal with this chlorine that's attached, and so we need to write chloro in front of the parent name to say that there is a chlorine atom attached to the methane. So this is chloromethane. Okay, the next molecule here, 1, 2, 3 carbons in a row. We also have this functional group here, a carbon-carbon double bond. So let's see if we can find the name for this molecule. Now, it has 3 carbons in a row, so it's prop, and it has the carbon-carbon double bond here, so the end is ene. Now remember, so because we have now have the parent name of propene, we don't need to actually deal with the double bond again because we've already shown that it's in this molecule by calling this propene. And that's how we name these molecules. Okay, so let's look at some more complex molecules to name. So we've gone over how we might name the parent chain and how we might name if there's one simple functional group coming off. But what happens if the functional group is on a particular part of the molecule and we need to show where it is on the molecule? Well, what we have to do is we actually have to give a number to the carbon that it comes off. Now let's have a look at this with these 2 molecules here. So these 2 molecules look similar. They both have chlorine substituents, chlorine functional groups coming off the chain. But the one on the left, and they both have 3 carbons in a row, right? So they're both chloropropane, but as we can see, they're different. This chlorine comes off the middle and this chlorine comes off the end. So how do we show that difference? What we do is this is propane, like I said. And how do we show the difference? We do the following. We number it. So I start from the end that is closest to the functional group, and in this case, in this first molecule, it doesn't matter if I start from the left or the right, but I have 1, 2, but so the second carbon, or carbon number 2, is where the chlorine is attached, or the chloro group. So when I name this, instead of just writing chloropropane, I'm going to write 2-chloropropane. Always put a hyphen between the number and the letter. Okay. The next one, if you see, if we try and number this and we number from the side that's closest to where the chlorine is attached, we only need to number the first carbon. So the chlorine is coming off the first carbon, so this is called 1-chloropropane. Now, because the names are slightly different, one is 2-chloropropane and one is 1-chloropropane, we can distinguish between these two molecules that are similar to each other. Let's have another look at another molecule. So this molecule here, we have a CH3 substituent coming off. Now, let's go through and see if we can name this systematically. Let's get the parent name for this. We know there's a methyl group coming off. There are 5 carbons in a row, right? So it's going to be called pent, and there's only carbon-hydrogen bonds or carbon-carbon single bonds, so it's going to be ane. So this is called pentane, but now remember I have to show that it has this methyl group coming off. Now what we might initially do is we might count from the left, 1, 2, 3, 4, and say it's 4-methyl pentane. But that's not how we name organic molecules, because if we were to see this organic molecule in 3 dimensions and we viewed it from the other side, it would actually be coming off the second one. And the rule here is we always number when we name so that it has the smallest possible number that we could give it. So we're actually going to number from the right hand side, because if we do it that way, then the number of the carbon the substituent is attached to is number 2, and this is called 2-chloropentane. Okay, let's have a look at the next molecule. So in this case, this molecule has 2 different substituents coming off the chain, and we have to number the chain in such a way that they get the smallest possible number, but also apart from that, once we've done that, we need to, if we have to make a choice between the chlorine and the methyl group, we need to work out which one has the higher priority for the lowest number. I'll show you what I mean by that. So we have a chlorine and a methyl functional group with 4 carbons in a row, so it's going to be bute. It doesn't have a specific functional group that changes its suffix, so it's going to be butane, right? And now we have to number it. Now, which one of these two, the methyl group or the chloro group, has a higher priority? And we can see in our table here that actually the halogens have a higher priority than the alkyl groups. So the chlorine is we're going to make sure that when we number this, we're going to number it from the left, so it gets 1, 2, 3. So it gets number 2 and methyl gets number 3, and not the other way where methyl will get number 2, because chlorine is a higher priority. So if we go to number this now, we get 1, 2, 3. So we're going to have 2-chloro, 3-methyl pentane. And again, make sure that we have a hyphen in between the numbers and the letters, and also make sure that our first part of our name is right up next to the parent chain part of the name. There is no space left in between there. Okay, let's continue to look at numbering here. So we're looking at how we would apply numbering when naming more complex organic molecules. So let's have a look at this first molecule at the top here. This has 5 carbons in a row, so it's going to be called pent, and it has 2 different substituents coming off, a CH3 that is a methyl group, and an NH2 that is an amine group. Now notice when we look at the amines here, that the amines actually have a suffix. So if you have a suffix, you are going to change the name of the parent chain. And we are going to, before we write the name of the parent chain, we have to work out what number the NH2 is attached to. And we can see that the NH2 is attached to the 3rd carbon. So this the parent name for this molecule is pentanamine, but pentan-3-amine. Okay, and the 3 shows us where the NH3 is attached on the parent chain. Now, we also have to show that we have this methyl group, so we're going to write that as a prefix in front of the parent name, and it's going to be called 2-methyl pentan-3-amine. Okay, let's have a look at the next molecule that we have here. The next molecule we have is this one here. We can see that there are 4 carbons in a row. There is that's going to have bute as the start of its name. There is a functional group here with a double bond carbon, and there is a functional group here that is a fluorine. Okay, now because the double bond carbon has an associated suffix with it, it's going to change the parent name. So this is going to be butene. Now I have to say where the double bond is, because the double bond is on the attached to the first carbon. It could be if I just had butene attached to the second carbon. So in this case, I'm going to call it but1ene. Now I also now have to say just have to name the fluorine group here, and we remember that it has the prefix fluoro. It's coming off the third carbon, so this is going to be 3-fluoro-but1ene. Okay, the last molecule here, the last molecule has one substituent and one group on the end, functional group. Now we have 3 carbons in a row, so it's going to be prop. It has a methyl substituent coming off here and a carboxylic acid functional group. It so happens that the carboxylic acid is the most important or the highest priority functional group, so it will change the name of the parent chain here to propanoic acid. Now for a carboxylic acid, I never have to write the number that it is, because a carboxylic acid, because it's the highest priority, will always be number 1. So the parent part of the name here is propanoic acid. But remember, we have the substituent coming off, and because the carboxylic acid is the highest priority, that carbon is 1 and the next carbon is 2. So the methyl group is coming off the second carbon, and this is 2-methyl propanoic acid. Okay, so let's continue to look at naming organic compounds. In this part of the video, we're going to go now and look at what if we have multiple identical substituents? How are we supposed to write that? And we're going to learn about the prefixes di, tri, and tetra that are used in front of the substituent name or the prefix name at the front. So here's the first molecule. We can see that it is 4 carbons long, so it's going to have the prefix but for the parent part of its name. It has 2 different functional groups, substituents, coming off the 2 carbons in the middle. And remember, they're called chloro. It has no other functional groups that change its suffix, so it's going to have the parent name butane. Now, we might write this, we might go 1, 2, 3 and call it 2-chloro, 3-chlorobutane. But chemists think that's kind of clumsy, so what they do instead of writing 2-chloro, 3-chloro is they write 2, 3 dichlorobutane, and that is the correct way of writing it. So we've condensed the longer form of the name down to a shorter one, and we put a di if there are 2 of the same group. Let's have a look at the next molecule that we have here. So in this molecule, we can see it's also going to have 4 carbons. It is a butane as well. It's got 3 chlorine functional group substituents, and it's going to have the parent butane again, but because it has 3 chlorine substituents, instead of writing di, now we're going to write tri for 3. So 1, 2 are the places that the chlorines are attached to. There was 1 attached to 1, and there are 2 attached to the 2 carbon. So this ends up being 1, 2, 2 trichlorobutane. We have to, for each different functional group or substituent coming off, they must have a number associated with them. You just can't write 1, 2 trichlorobutane. You have to say specifically where each of them are using the numbers. Okay, so, and this is what we use the tri here. Remember to say that there were 3 of them. Okay, so the last one here on this part of the video, we have 3 carbons in a row. This is going to be prop. 2 methyl groups coming off, propane is going to be the parent chain here, and we have these carbons coming off the second, these methyl groups coming off the second carbon. Now, this one's kind of interesting because we could call it 2,2-dimethyl propane, but actually in this case, there is only one way that you can attach two methyl groups to a propane molecule and it still be a dimethyl propane. So actually it's okay not to put the numbers here because we couldn't attach the methyl groups to the front of the molecule because they wouldn't be a propane anymore, they would be a butane. So often when it's evident exactly, it's self-evident where they are, we don't have to write the numbers. So in this case, it's just called dimethyl propane. Now, if you find that you're not sure about when to do that, don't worry about it. If you put the numbers, you won't be wrong. Okay, so the final bit of the final rule, the sixth rule we need to remember for naming organic compounds is when we write the functional groups or substituents at the front of our name, okay, the front of the parent name, they have to be written in alphabetical order. Okay, so what do I mean by this? Well, let's have a look at this first molecule. First molecule, 4 carbons, it's going to be bute. It's got a chlorine group and a methyl group. Okay, methyl group, chlorine group. There isn't, none of these substituents change the suffix on the parent name, so it's just going to be butane. But now we have a chloro and a methyl, and you can see that the chloro, the C is before the alphabet compared to the M, so we are going to write the chloro substituent first. So they both have the number 2, so it's going to be 2-chloro, 2-methyl. If you had written it 2-methyl, 2-chloro, you would have been incorrect. Okay, so the next one here, let's have a look. We have 1, 2, 3, 4, 5, 6 carbons in a row. 1, 2, 3, 4, 5, 6. So this is going to be a hexane, and it has a fluoro and a chloro functional group. And because there are no other suffixes here, it's going to be called hexane as its parent name. Now, if we look at these two here, chloro and fluoro, chloro comes before fluoro in the alphabet. So we number this first. So 1, 2, 3. So even though the chloro has a higher number, it is going to be written first because we have to write it in alphabetical order. So we have 3-chloro, 1-fluorohexane. Okay, let's have a look at this last molecule. This last molecule is a bit busy. We have 3 carbons. It's going to be prop. We have this enoic acid here, so that, remember, that's the most important. So this is, it has a chlorine, a chloro group, and it has these bromine groups here. Now, this parent name for this is propanoic acid. Now, if we look down the bottom here, the chloro and the bromo, we ignore the priorities, and actually for the halogens, it's not important about which is more, they are not actually in priority order because we're just going to number that when we actually write these out, we're going to write them in that the bromo is first because it comes in the alphabet first. Now remember, we name from a carboxylic acid, we start from the highest priority, carboxylic acid, carbon. So we start 1, 2, 3. And so because we're doing the bromines first, because they start with B instead of C, we're going to say 2, 3, dibromo, 2-chloro, propanoic acid. Okay, it looks kind of tricky, when we first look at them. But if you practice them, you will get better at this. Right, so I've got 3 more complicated molecules that we're going to look at. And we're just going to see some points or some advice on how we would write correct names for them. We're going to use all of the 6 rules we've learned so far. Let's start with the first molecule here. Okay, so what we can see here is actually the longest chain of carbons is not the chain just horizontally along here with 5 in it, but it's with 6 in it. So this is going to have the prefix hex. we can see that there are two substituents coming off, a CH3 and an amine functional group. We can also see that the amine functional group will change the suffix on the parent name, and it's going to change it to hexanamine. But because we need to specify what number carbon it comes off, we have to number this chain. And remember, we have to number in such a way that the amine group will have the smallest possible number it can. And that means we have to number from the top and not from the right. We can't number from the left because the CH3 on the left is not in the longest chain. So we number from the right, 1, 2, 3. So the parent chain now has the name hexan 3-amine. Now we have to name the substituent, other substituent coming off the CH3, the methyl group, and it's coming off the third carbon as well, so it's 3-methyl hexan 3-amine. Let's look at the next molecule. So the next molecule is interesting. There are two functional groups, and both of these functional groups could possibly change the suffix on the parent name. But let's have a look at that. We have 5 carbons in a row, so it's pent, and we have this carboxylic acid functional group and this amine functional group. The carboxylic acid functional group has the suffix enoic acid, and the amine functional group has the suffix enamine. However, because the carboxylic acid functional group is a higher priority than the amine, then the amine functional group is actually, or the amine is going to be named using the prefix in front of the parent name. So we're going to name this pentanoic acid because remember, the carboxylic acid has the higher priority. And then we're going to number 1, 2, 3, and we're going to name the amine as this functional group using the prefix, right? So it's going to be 4-amino pentanoic acid. The next thing that we're going to do here, the next molecule, is this one here. When we look at this molecule, we can see that there are 3 carbons in a row and there are 2 functional groups again. So there is a prop, an OH functional group, an amine functional group. So we have a hydroxy and an amino. But the hydroxy or the alcohol is a higher priority, so the parent name will have the suffix enol here. So we are going to number this 1, 2, and this is going to be called propan 2-ol, and then we are going to give the functional group of the amine, which is 2-amino, 2-amino propan 2-ol. So I guess the important thing to note here is if you actually, and it's really going to be amines and alcohols that we look at, but if the suffix on the parent chain is already used, because let's say that it's an alkene or it's a carboxylic acid or something like that, then actually we're going to put them as a prefix. Now note, even though the alcohol has a higher priority than an alkene, because the alkene doesn't have a prefix, it's always going to be written on the end of the molecule. So if we find an alkene, we're going to have to give the alcohol writer as a prefix instead of a suffix. And that's kind of the end of what we need to know for level 2 naming. Have a look on the next part of this video and see if you can name the molecules that I give you. Okay, so here are just 6 molecules, organic molecules. They're drawn in a condensed form. That is, we're not showing the hydrogens bonded in the north, west, south, east position. We're just sort of collapsing them up, but we know that's how that they would be. And what you need to be able to do is see if you can name each one of these molecules, and then for the names down the bottom, can you draw the molecules? So what you might want to do, just pause the video and then I'll go through and say what the names are. Okay, so let's go and have a look at these names. So the first one here, 1, 2, 3, 4 carbons in a row. There is no other functional groups, so it's going to be butane. This one here also has 1, 2, 3, 4 carbons in a row. However, it has a methyl functional group and it's coming off 1, 2, the second carbon, so it's going to be 2-methyl butane.
Okay, if we look at the next molecule, we have 1, 2, 3, 4, 5 carbons in a row. We have a double bond coming off the first carbon. Now, because the double bond is a higher priority than the methyl group that's coming off here, we're going to number from the double bond side. So we have 1, 2, 3, 4. The double bond is coming off 1, and the methyl group is coming off 4. So this is 4-methyl pent 1-ene. So the next one we have here, chloromethane. Okay, with chloro group coming off a methyl. Don't need a number because it's the only place it can come off is number 1. The next one, we have 1, 2, 3, 4, 5. So this is going to be pentane. There is a chloro group coming off, but that doesn't give us a change to the suffix, and it's coming off the third carbon, 3-chloropentane. The last one, 1 carbon, has the functional group COOH, so it's enoic acid, which is methanoic acid. Okay, so now we have to draw propane. Go down the bottom, it's prop. It's only got single bonds, so we're going to draw it like this. The next one, 2-methyl hexane. Hexane, go down the bottom and have a look, 6 carbons in a row, and off the second one, we're going to draw a methyl group. Propan 2-ol, we're going to draw 3 carbons in a row and an OH group off the second carbon. 1 bromobutane, butane, 4 carbons in a row, and a bromine group off the first one. Hexanthreamine, 6 carbons in a row, and an amine group coming off the third carbon. Butanoic acid, 4 carbons in a row, carboxylic acid, always off the first carbon. Look, I find that the drawing is a lot easier. We're just following the instructions they give us. We just have to be a lot more careful with the naming. Hopefully that has helped you go over your naming. Look out for the extra videos that I'll give you with examples on how to name. Okay, so at the end of this video, I want you to feel confident to draw the constitutional isomers from a molecular formula. So what are constitutional or structural isomers? So any organic molecule that has, or any organic molecules that have the same molecular formula, in this case, let's say C4H10, but different structural formulas, they are arranged in different ways, are called constitutional isomers or structural isomers. Let's have a look at what I mean by this. So if we want to draw a constitutional isomer for a molecule, let's say C4H10, the first thing we have to do is draw the simplest one, and it's usually the one with the longest chain, 4 carbons in a row. So I usually just draw the 4 carbons joined together without drawing the hydrogens or anything else, just so I can visualize it. So that's my first possible way of connecting them. But I could also maybe do 3 carbons in a row, okay, and a carbon off the middle. Now, if I was to just do, that's the only way that I can arrange the molecule when I have 3 carbons in a row. If I was to do 2 carbons in a row, well, I can't draw another way of drawing the isomer here, because 2 carbons in a row with a carbon coming off it is really not 2 in a row. It would end up being 3 in a row. So these are the 2 only possible constitutional isomers or structural isomers I can get for C4H10. So I'm going to draw them out fully now. Here's the first one. We can see that that's butane. And here's the second one. We can see that that one there is going to be methyl propane. Now, the last, I would suggest that you go through these 4 points every time you draw your constitutional isomers. You start with just the frame, then you draw the, so you start with the longest one, then you go down to the second longest one, you draw as many as you can, then you draw the complete structures, and then you name them. Now you will know that they are actually different isomers if they have different names. It will verify, because you can't have, let's say you could draw these slightly different, you could draw them bent, but when you went to name them, they would have the same name. So because they have a different name, it means that they must be isomers. Let's have a look at an example of a problem that you might get. Example, draw the structural isomers for C4H9Br. Okay, so if we start with my first rule here, we're going to draw 4 in a row, okay, and put the bromine in as many different positions as we can. So I can put the bromine coming off the first carbon, or I can put the bromine coming off the second carbon. What I can't do is draw another one with a bromine coming off the third carbon, because that would be the same as the bromine coming off the second carbon, just flipped around, and it would have the same name, because this one here would have the name 2-bromo butane, but if I had it coming off the third carbon, I would number from the right and it would still be 2-bromo butane. So those are the two possible ones we can have with a chain of 4. Let's do a chain of 3. I can either do the bromine here coming off the end, or I can do the bromine here coming off the middle. Okay, so this is a primary haloalkane and this is a tertiary. Now I can't do chains of 2 because that I would always be adding a carbon to the end of the chain. So these are only the 4 structural isomers I can have for this molecule. So the next step I'm going to draw is draw them out. Okay, so here's this one drawn out, the second one, the third one, and the fourth one. Now when I name these, they should have completely unique names to each other. So the first one is 1-bromo butane. The second one, 2-bromo butane. Okay, we started quite well. The third one is 3 carbons in a row, a methyl group and a bromo group. So remember, we're going to write the bromo first. So it's going to be 1-bromo, 2-methyl, 1-bromo, 2-methyl propane. And the last one is going to be 2-bromo, 2-methyl propane. And there we have it. We've drawn 4 constitutional structural isomers. And if you take this approach anytime that you have to do it, you're going to be amazing with it. Okay, so this video is going to go over stereoisomers and geometric isomers. By the end of this video, you want to be able to draw and recognize geometric isomers and explain why they can be geometric or stereoisomers. Okay, so let's just have a talk about it for a start. So when we actually have a single bonded molecule, what happens is any groups or atoms on either side of the single bond can actually freely rotate 360 degrees. So none of these substituents are either held at the top or the bottom of the molecule. They can move about easily. So we can't get geometric isomers or stereoisomers with saturated compounds. However, what we can do is if we have a double bond, then a double bond will, here we can see, hold these different groups firmly in place. Now what do we mean by that? Well, because these carbons have 2 bonds between them, the right hand side of this molecule and the left hand side of the molecule can't rotate relative to each other. So the CH3s are always going to be held at the top of the molecule or on the same side of the double bond as each other. Now let's have a look at some geometric isomers, and in this case we're going to have a look at the geometric isomers for butyrene. So actually the first geometric isomer for butyrene is the one we've just drawn. Notice it's butyrene because there are 4 carbons in a row and the double bond is off the second carbon. But in this arrangement here, because of the double bond, the 2 methyl groups have found themselves at the top, and this is actually called this has a special name, it's called cis, but we'll just go through this first. So we can see that off the first carbon there are 2 different groups or atoms bonded to it. So there's a CH3 and there's an H. And off the second carbon, there are 2 different atoms or groups. There's a CH3 and an H. To be a geometric isomer, actually, you have to have 2 things. You must have a double bond to hold the atoms firmly in place, and each carbon of the double bond must have 2 different groups or atoms coming off it, so that we can get either a cis arrangement like this. Okay, so this is called cis butyrene, or we can get this trans arrangement like this, trans-butyrene. Now notice these molecules actually have a different shape. This is like if you were to see this molecule, it would be a U shape, and this is kind of like more of a straight line. Now, when would we have a double bond but not have geometric isomers? Well, let's have a look at this one here for propene. Now, if you look at propene here, you can see, well, it does have a double bond and it is holding the CH3 at the bottom of the molecule. And it's holding these two hydrogens at the top together. However, because on the left-hand side, the carbon has two atoms that are the same, it cannot be a geometric isomer. We can't have a cis arrangement and a trans arrangement because actually the hydrogens are in a trans arrangement, but they're also in a cis arrangement. So there's only one version of this that we can draw. It can't be geometric isomers. So there must be two requirements for geometric isomer. The first requirement is there must be a double bond, because it stops the molecule from rotating and holds the groups and atoms firmly in place. And it must have different atoms or groups coming off each carbon of the double bond. If you meet those two requirements, you will have both a cis version and a trans version. They are geometric isomers or stereoisomers. Okay, so what type of question are they going to ask you about this? Well, here's a question here. Explain why 1,2-dichloropropene has geometric isomers. Draw and identify these isomers as cis or trans. Okay, so here is a drawing of 1,2-dichloropropene. And I've drawn the trans version of it because the chlorine atoms that are similar across the double bond are trans from each other. Notice that this meets the requirements. It has a double bond that stops rotation, holds them firmly in place. And we have off each carbon of the double bond two different groups coming off it. So that's the trans arrangement, and here's the cis arrangement. So we are trans and cis. Now we will need to explain why this is trans and cis. Well, both carbons of the double bond here have two different groups, atoms coming off them. The carbon 1 here has a hydrogen, a Cl and a hydrogen group coming off it. And the carbon 2 has a CH3 and a chlorine coming off it. As the double bond holds these groups in a set position, we can either get a cis or a trans arrangement as shown. So when I explain this, I actually have to explain in detail, yes, it has a double bond that holds them firmly in place, but the first carbon has a chlorine and a hydrogen that are different, and the second carbon has a CH3 and a chlorine that are different. So I actually have to expand and explain to whoever's asking me the question how I know it's a geometric isomer. Okay, one last point about geometric isomers. You might not notice this, but chlorines are very electronegative atoms, and actually the trans molecule here is, if we were to take the center of the negative charge, it's right in the center, so this is really a non-polar molecule. But if we look at the cis one, two chlorines at the top means the center of the negative charge in this molecule is going to be near the top of this molecule, and it's going to be polar. And because of that, they're going to have slightly different boiling points and melting points. And actually the boiling point of the trans one is 48 degrees Celsius, where the boiling point of the cis one, because it's polar and it will have slightly stronger intermolecular attractions, it has a higher boiling point. So that's one of the important reasons we want to know the difference between, or know whether it's a cis or a trans geometric isomer. Hopefully this has helped you and you now have a better understanding of geometric isomerism. Okay, how do we classify alcohols and haloalkanes? So we can classify haloalkanes and alcohols as either primary, secondary or tertiary depending on where their functional group is attached. What do I mean by this? Well, here is an example of a primary haloalkane. So it's a primary haloalkane because the bromine functional group, the halogen, is the carbon that it is attached to. That's this carbon, let's just see, this carbon that we've just shown here. It is bonded to one other carbon. So we're looking at the carbon that the halogen is attached to. How many other carbons is it bonded to? It's bonded to 1, so this is called a primary haloalkane. Well, in this next example, here is an alcohol. Now you can see that the alcohol functional group is at the top here, and it's bonded to this carbon in the middle. Now that carbon in the middle is itself bonded to 2 other carbons. Because the carbon that is bonded to the functional group is bonded to 2 other carbons, it's classified as a secondary alcohol. Now a tertiary is when the carbon that's bonded to the functional group is bonded to 3 other carbons. So here the functional group is a chlorine. The carbon it's attached to is right here in the middle, and there are 1, 2, 3 other carbons attached to the carbon that is attached to the functional group. That makes this a tertiary haloalkane. Primary, secondary, tertiary, and we identify and classify them based on how many carbons are attached to the carbon that is joined to the functional group. So this is a type of question we might be asked. 2-chlorobutane is a secondary haloalkane. Draw a tertiary structural isomer of 2-chlorobutane and explain why it is called tertiary. So here's here is the structure of the isomer of 2-chlorobutane. So what is an isomer? A structural isomer is you have the same formula, the same number and type of atoms, the same molecular formula, but they're arranged in a different way. So instead of having 4 carbons in a row with the chlorine coming off the second carbon, what I've drawn here is a isomer of it that is tertiary. Now it is tertiary because the carbon in the center that's bonded to the chlorine is 3 carbons attached to it. And I explain this because it's asked me to explain why it's classified as tertiary. This is a tertiary haloalkane as the chlorine functional group is attached to a carbon which itself is attached to 3 other carbons. And that's the type of question you might have to answer on classifying something as a primary, secondary, or tertiary. Draw whether it's primary, secondary, or tertiary, and say why it's primary, secondary, or tertiary. Okay, in this short video, I'm going to go over addition reactions, what they are and how they happen. So addition reactions are a specific type of organic reaction that involve the reactant having a double bond or possibly a triple bond. Now, the reason that alkenes that have double bonds can undergo addition reactions is that the double bond will break and then it will form 2 new attachments. And because we're adding 2 new atoms or groups to it, it's called addition because we're adding. Now, every time that we do a specific type of addition reaction, we're going to have an associated reagent. And you can see that I've got 5 different addition reactions shown here in this table. Hydrogenation, halogenation, 2 different types of halogenation here, hydration and addition polymerization. But let's have a look at each one of these examples. So in the hydrogenation, we're going to start with an alkene and we're going to have as a product an alkane. And so what happens here is, here's an alkene, this is pent-1-ene. We're going to add the reagent, which is hydrogen gas. Now, there are 2 versions of reagent we can use here, and we have to be familiar with. The first, so remember we need a double bond, and the reagent is hydrogen with platinum, or it could be hydrogen with nickel over here. Now, if we break this double bond here, what's going to happen is we are going to join on the second carbon and the first carbon, and what we're adding to this are hydrogens. That's what the H2 is. Now, whenever we write the reagent and we put H2 and then /PT, the thing on the left hand side of the / is what we're actually adding, and the thing on the right hand side is the catalyst. So we're adding hydrogens and H2, which means we're going to add a hydrogen to each place where the double bond is, and then we end up with this molecule, which is going to be an alkane. Actually, in this case, it's pentane. So this is hydrogenation because we're adding hydrogens to the carbons that were part of the double bond. The next one is called halogenation. So in this case, in halogenation, we're going to add halogens. Now, the first example I'm going to give you is we add a diatomic molecule of halogens, or two halogens joined together in a molecule, and we either use chlorine, bromine, or fluorine. They'll write whatever halogen is above the arrow. Remember, again, the double bond is going to break at the point the double bond is going to break between the two carbons, and that's where we're going to attach them. Now, we don't have a catalyst with the bromine, they're quite reactive, so it will break this double bond, and we will add one bromine atom each to where the double bond was broken, and there we get. And here we get a haloalkane, and of course this is going to be called 2,3-dibromobutane. Okay, so the next type of way that we can carry out a halogenation is we can add hydrogen chloride, hydrogen bromide, or hydrogen fluoride. So that is a molecule that has a hydrogen and a halogen attached. In this case, we're using hydrogen fluoride. So if we break this double bond, of course, we have two atoms available to attach, a hydrogen and a fluorine. And so we add the hydrogen and we add the fluorine. Now, actually, sometimes we have an issue when we break the bond. If the organic molecule, sorry, the alkene is asymmetric, we have to decide what side we put the fluorine and what side we put the hydrogen. And in fact, in a later video, we're going to learn about Markovnikov's rule that explains how we identify which one will happen. So that's the two types of halogen reactions. The next one is called a hydration reaction. So we're adding water, okay, to the molecule, and in fact when we use a reagent to add water, it actually has to be in acidic condition, so we add H2O/H+. So you can either write that as the reagent, or you can write dilute H2SO4, or sometimes H2SO4 brackets aqueous. In this example that I'm giving you here, I've got H2O with the dilute acid as the catalyst. Now remember, it's the thing on the left hand side of the / that we're adding, and what we have here is an H and an OH that has been added. Okay, so if you could split the H2O molecule in two, however you break it, it's always going to break into a hydrogen and an OH. So we add a hydrogen to one side and an OH to the other, to the double bond once we've broken it. So here we get, we have now produced an alcohol molecule, right? Now, interestingly, most of the time the OH will attach to the middle carbon here. And remember, there's a rule as to why it does this, and this is called Markovnikov's rule, but we'll learn this later. And the last one is called an addition polymerization. Now, addition polymerization is when we take a large number of alkenes and we break the double bond, and then what happens is we join them all together in a long chain. So here, if we break the double bond, we would join it together where the double bond was broken, exactly the same way as we did in the others, but we would form a long chain when it's under heat and it has a catalyst. So the long chain we form here is, the wee squiggly line means that it is a chain that continues on for hundreds of atoms. Okay, so it's not the end of the chain, it just continues, and I'm just showing so many of these units repeating here. And those are the different types of addition reactions we have to be able to do at this level: hydrogenation, halogenation, hydration, and addition polymerization. Now, when you have to justify and say what type of reaction is happening, you can just say each one of these is an addition reaction. And remember, addition reactions have double bonds, the double bonds break, and the atoms or groups attached to the carbons where the double bond had broken. Okay, and that's the end of the video. Okay, so in this video, what I've given you here are 5 different reaction schemes. You've got A, B, C, D, and E, and what you need to do is supply the missing information. That's either going to be what is the reactant that's missing, what's the product that's missing, can you give the reaction type, or can you give the reagent that's missing. So let's have a look at the reaction scheme A, which is problem A. So here what we're given in problem A is we're given propene as our reactant, and we're given a reagent of H2/Ni. So remember the reagent here, H2/Ni, means that hydrogen is being added, Ni is the catalyst. So the type of reaction that's happening here is an addition reaction, and remember we're adding hydrogens, we're breaking the double bond and adding the hydrogens, so our product is going to be propane. Okay, problem B. In problem B, in this reaction scheme here, they've given us the reactant and they've given us the product. So if we look carefully at the difference between the reactant and product, we can see that a hydrogen and a fluoride has been added. So this is an addition reaction, and where the reagent we're going to use here is hydrogen fluoride, and that's what is missing. For problem C, we can see that the product here is 1,2-dichlorobutane. We've added a reagent of Cl2. So the Cl2 is what we add when we want to add to a double bond. So this is an addition reaction, and our reactant is going to be the double bond is going to come off the first carbon, and we have but-1-ene here. For problem C, straightforward here, they've given us the reactant and they've given us the reagent, H2O, and it's in acidic conditions /H+. So we know because it's H2O, we're going to add a hydrogen to one of the carbons and an OH to the other. But because we are adding to either carbon 1 or 2, there are two different products, because we can either add the hydrogen to the first carbon, and in that case we would get butane-2-ol, or we could add the hydrogen to the second carbon, and in that case we would get butane-1-ol. So there are two possible products here, because, and the reason for this is this alkene here is asymmetric. That is, and we're adding a reagent that has two possible groups atoms being added. So the last problem, they've given us the two possible products, and they've said it's an addition reaction. So what would have the alkene been that could have made those two possible products, and what is the reagent that we would have added? So the alkene for problem E is pent-1-ene, and the reagent here is going to be hydrogen bromide. And those are four reaction schemes, and they all involve addition reactions, where we have had to work out through a problem-solving technique what the addition, what type of reaction, what type of reagent, and what the products or reactants are. Hopefully this has been helpful, and good luck with your rest of your chemistry studies. Okay, so in this video we're going to go over a specific type of addition reactions. That's addition reactions of hydrogen halides and water to asymmetric alkenes. Okay, first up, let's look what happens when we add hydrogen chloride, that's our hydrogen halide, to a symmetric alkene. Now, when we talk about symmetric, we're really looking at the middle of the double bond, and if we rotate this 180 degrees, will it end up looking exactly the same? And you can see that this molecule does. Now, in this case, what's going to happen is that we are going to break the double bond, and we're going to attach a hydrogen from the hydrogen chloride and a chloride at each one of these carbons, either the second carbon, this one here, number 2 carbon, and we numbered that from the edge, or in fact the other carbon is number 2 as well, because if we numbered it first it would also be number 2. So what happens is we could either put the hydrogen up here, or we could put the hydrogen down here. We can have the hydrogen coming off the second carbon on the left and the chlorine off the third carbon, or we can have the hydrogen coming off the second carbon on the right and the chlorine off the other carbon. So the first one would be called 2-chlorobutane, but because this molecule is just this molecule rotated around, it's also called 2-chlorobutane. So whether we put the chlorine off this first carbon here or the second one here, we are going to create exactly the same molecule, and so it doesn't matter where the chlorine attaches on the first symmetrical molecule, where the hydrogen will always get just one type of product. However, let's have a look at an asymmetric alkene, because in an asymmetric alkene we have two possible products. So here is an asymmetric alkene. So again, if we put a rotational point in the middle of the double bond and we rotate it around, they wouldn't superimpose on top of each other. That makes this alkene asymmetric. And we're especially going to recognize asymmetric alkenes and use this rule when we see the double bond on the first carbon. So we're going to add a hydrogen to one of the carbons and a chlorine to the other. See what happens here. So we've got the first and the second carbon to choose from. So the chlorine can either attach to the first carbon or to the second carbon. So in this case, the chlorine is attached to the second carbon, and that means this is going to be called 2-chlorobutane, just like in our previous equation. But in the other option, the chlorine can attach to the carbon that was the double bond on the first carbon. So this is 1-chlorobutane. And what we note here is because this molecule was asymmetric, we now produce two different products. Now, which one of these products is more likely to occur? Well, we use a rule called Markovnikov's rule to work out which one will happen the majority of the time. Markovnikov's rule is as following. The majority of the time, the hydrogen atom will attach to the carbon that has the most hydrogens attached to it already. In this asymmetric example on the top here, the carbon that has the most hydrogens is carbon 1, and the carbon that has the least is carbon 2. So for the majority of the time, the hydrogen will attach to 1 and we will get 2-chlorobutane. The minority of the time, the hydrogen will attach to carbon 2 and the chlorine to carbon 1, and we'll get 1-chlorobutane. Now what they mean by majority and minority is if there were 1,000 of these molecules and the reaction happened 1,000 times, you might get 750 of 2-chlorobutane the majority of the time, and 250 of 1-chlorobutane. One is more likely to happen than the other. So, explain why but-1-ene forms two different products when it is reacted with H2O, H+. Now we can see that H2O obviously breaks apart to make OH- and H. And remember that H is going to attach to the carbon that has the most H's the majority of the time. So here's an example of the equation. Let's draw that first. What we can see here is that we have two carbons, 1 and 2. We can call one carbon the richer carbon. And Markovnikov had this sort of wee phrase to remember, the rich get richer. So the carbon that is the richest here is the one that has the most hydrogens. So it is rich. So that's the carbon that's going to have the hydrogen bond to it the majority of the time. And remember, if the hydrogen bonds to carbon 1, the OH is going to bond to carbon 2. And this is going to be our major product. It happens most of the time. And less often, the minority of the time, the hydrogen will bond to carbon 2 and the hydroxide will bond to carbon 1. And this is the minor product. So here we've drawn an equation to show what happens, but our example has asked us to explain why. So now we're going to write an explanation, and we'll say something like the double bond between carbon 1 and 2, there are two carbons that the hydrogen can bond to when the double bond is broken. The majority of the time the hydrogen will bond to carbon 1. Notice I'm being specific on which carbon it is that will be the majority. And it has more atoms attached to it, right? That's why, because we don't say it's because the rich get richer. We actually have to be quite specific here and say it's the carbon that had the most hydrogens bonded to it. That's why the hydrogen will bond to it the majority of the time. The OH will bond to the C2 carbon, forming the major product, butan-2-ol. See, this is butan-2-ol. The minor product is butan-1-ol, and it will be formed when the hydrogen bonds to the second carbon. So that's our explanation. And that's asymmetric alkanes, how we add hydrogen halides or water using Markovnikov's rule. Good luck. Okay, in this video we're going to go over addition polymerization. So let's get started. So here is a monomer or an alkene that could be under heat and pressure combined with other similar alkenes or identical ones to form a long chain. Now, when this is put under heat and a catalyst, what's going to happen is this double bond is going to break. And this individual unit is called a monomer because it's made up of one unit. The N here represents, the N down the bottom here, represents how many of these units would have. So it could be a number like 100, or it could be 500, or it could be 1,000, because we produce actually very long chains of these polymers. So what the first step that happens to this is that the catalyst will help the double bond break, and it will break into these intermediate molecules. They're called the radicals. Radicals because the bond is broken and the carbons are just left with one electron each, and they're looking to make another bond. And what happens is these carbons are going to form another bond, but they'll form a single bond to the adjacent carbon. So we've broken the double bond, and now they're looking to form a single bond. And what they're going to do is form a repeating chain of these units. So here's our polymer. Here is one of the repeating units. Notice that this is the same as what our monomer was, apart from the double bond has been broken and it's made a bond to the left and to the right. So this repeating unit will repeat again and again down the polymer. And at the end of the polymer, I just draw an open bond. Often I just a squiggly bond here to show that it continues in a long chain. So when we actually draw these addition polymerization reactions, we are going to just draw the monomer and the polymer, and we don't draw the intermediate. The intermediate here is just to show you the type of way that this reaction actually happens, the mechanism for it. So the initial monomer are very reactive because they have carbon-carbon double bonds. And having a double bond leaves molecules open to have addition reactions, making them very reactive. Because they have double bonds, they're said to be unsaturated. Now, the resulting polymer here does not have any double bonds. It only has single bonds, and it's said to be saturated. And because it only has single bonds, it will not undergo addition reactions, and it is less reactive or more stable. These long chains form long string type units, like if you think about some spaghetti. And those, if you think about them in terms of pieces of spaghetti and long strains, they actually are attracted to other long strains and form weak attractions between them. And these weak forces between these long chains and the long chains being sort of mixed together give polymers their specific type of plastic properties. That is, they can be molded or bent because these long chains can slide past each other. So here's the type of question they might ask us about this. Draw the polymer formed when propene is heated with a catalyst. Draw 3 repeating units. So propene is this molecule here. I'm going to write down heat and catalyst, and they want us to draw 3 repeating units. So we're going to start with the squiggly wee bond, and we'll end with a squiggly wee bond, but we'll put 3 repeating units. Remember, we're going to break this bond here and then attach on the left and the right to the next unit. And this is what we get here. So what happens is the hydrogens get pushed up, and the CH3 and this hydrogen gets pushed, this hydrogen and the CH3 get pushed down, and we have these repeating units next to each other. Here is the repeating unit. You might just want to put a bracket around and say it's a repeating unit when you draw these. Sometimes they ask you to do that. So another type of question that they might ask you, this actual molecule here is called polypropene or polypropene. Sometimes people call it polypropylene. Okay, so the next one, they might ask you, draw and name the monomer that's formed from the polymer. So in this case, they have given us an example of the polymer. Now what we need to remember is this polymer has formed from a double bond that is broken and the carbon on each side of the double bond joining. So we always cut the polymer every 2 carbon atoms. So we cut it here and at the end. And then once we've cut it, we just form the double bond in between the 2 carbon atoms. So this is our repeating unit. This is what our monomer is going to look like. Apart from it will not have bonds to the right and left, it will have a double bond in the middle. And this here is the monomer that this forms. You can just imagine this 2 carbons and the hydrogen are actually just sticking up instead of being to the side. And that's addition polymerization. Hopefully that's been helpful. Look out for the other videos in this series, and I hope your study goes well. Okay, let's have a go and see if we can name some more organic molecules. So this is a reasonably straightforward, easy set of organic molecules to draw, 6 of them for a start and 6 of them to name. What I'd like you to do is just pause the video and then see if you can draw these molecules that I've written the name for here, and then name the molecules we've drawn. I'll then go through the answers in a couple of seconds. Okay, so the first molecule here is called propane, which means it's going to have 3 carbons in a row. Because it's an ane, and there is no prefix in front of it. There are no other functional groups. So it's just going to look like this, 3 carbons, propane. Second molecule, pentane, 3-methylpentane. So we're going to have 5 carbons in a row. We will have a methyl group. It's going to come off the 3rd carbon. And the molecule is going to look like this. But-1-ene. Okay, but, 4 carbons, ene, double bond. There is a double bond, there are 4 carbons, and the double bond comes off the 1st carbon. And this is what it looks like. The next one, 1-bromoethane. So, eth is 2, ane, it's going to be a chain of carbons and hydrogens, but there is a bromine coming off the 1st carbon. It will look like this. 2-fluorobutane. Butane, 4 carbons. Ane, there is a chain of single carbons with hydrogens, but there is a fluoro group coming off number 2. 1, 2. Propanoic acid. Okay, so propanoic acid has 3 carbons, but it has the functional group enoic acid, the COOH. So it's going to look like this. Okay, so let's name this molecule. They are drawn as a condensed molecular formula. So we have 1, 2, 3, 4, 5, 6, 7 carbons in a row. This is going to be heptane. Down here, hept. This one here has 1, 2, 3, 4, 5 carbons in the parent chain, and it has a methyl group substituent coming off the 1, 2, 3 carbon. So it's 3-methylpentane. This next molecule has 4 carbons in its chain, and it has the hydroxy group coming off the 1st carbon, but because it has a suffix here, this is now going to be called butan-1-ol. 1 depicts the carbon that the OH is attached to. We have 1, 2, 3, 4, 5, 6. We have 6 carbons in a row, so this is going to be hexane. And we have a chlorine group coming off the 2nd carbon, so it's 2-chlorohexane. The next one has 1, 2, 3 carbons in a row. So here, where are we here? Prop. It has an amine group. So an amine group is anamine. So it's off the 1st carbon, so it's going to be propan-1-amine. And the last one here is 1, 2, 3, 4, 5 carbons in a row. We have the pent carboxylic acid. It's going to be pentanoic acid. Hope you've had a great time reviewing your naming here, and I hope you got not 10 out of 12, 12 out of 12. Hey, look for my extra naming videos and look for the rest of the organic chemistry course that I've put online as videos. Right, let's have a look at elimination reactions. So we have elimination reactions that essentially when we take away two atoms or an atom in a group from an organic compound, and the places where those substituents were removed are going to turn into a double bond. Now, usually in this level, we are looking at what we call haloalkanes, that is chlorines, bromines, fluorines, iodines attached to a carbon, or alcohols, that's an OH group or hydroxy group attached to a carbon. So what we do is we remove one of those groups and an adjacent hydrogen. So here's two examples here that we can see. So here is a haloalkane. We have a fluorine, and what we're going to do here is we are adding potassium hydroxide. We could also add sodium hydroxide. Now in this case, to make this work as an elimination reaction, the potassium hydroxide has to be dissolved in alcohol and not in water. So we're using this reagent. What it will do is it's going to remove a fluorine that is attached to a carbon, and then remove a hydrogen from the adjacent carbon. And in this compound, the only adjacent carbon is the carbon on the left here. So we're going to remove this fluorine and this hydrogen. When we remove these two atoms, then what happens is a double bond is formed from the carbons that were removed from. And here we have. So you can notice in this example, there's only one way that this reaction can happen when we carry out the elimination. Notice here also there is an additional product that's produced, hydrogen fluoride here. These are the two things that have been removed and joined together. So let's have a look at our second example here. In the second example, we are adding concentrated sulfuric acid. Now, you might not know, but concentrated sulfuric acid has an affinity or really loves water. So it will try and take water away from any compound that we put it with, or it would dehydrate anything. So this is why we call the removal of an alcohol group and the hydrogen group from an alcohol a dehydration reaction. It's a type of elimination reaction because it's removing a water molecule. So essentially what happens here is we remove the OH here, functional group, and hydrogen from an adjacent carbon. In this case, there is either the carbon on the left or the carbon on the right. Now, because this molecule is symmetrical, it doesn't matter which one we remove it from. So we are going to, in this case, just remove it from the one on the right, and we'll produce this molecule here, which is propene. It has a double bond off the first carbon. It's also going to produce this product, water, that the sulfuric acid is becomes involved with. It's a combination of the OH and the hydrogen. Now, what's important with these types of elimination reactions to know is the following situation. And the following situation is when we have to use Zaitchev's rule. Now, Zaitchev's rule is that, look, if we have to remove either the halogen or the alcohol substituent, then the hydrogen is going to be removed from the adjacent carbon. We saw that in the two examples we're given. But the hydrogen that is going to be removed the most of the time is going to be the hydrogen that has the least, that is attached to a carbon, has the least hydrogens attached to it. So let's have a look at this example here. So you can see that there is a chlorine molecule, substituent atom attached to this carbon. Now there are two adjacent carbons. There's the one on the left and the one on the right. Now adjacent, I mean the carbons that are joined to the carbon that's joined to the halogen. Now the one on the left is said to be poor. Now the reason we say it's poor is because there are two hydrogens attached to this adjacent carbon, where the other adjacent carbon has 1, 2, 3. So this chlorine, okay, the functional group, the carbon that is attached to, if we look at the two carbons that are joined to it, we identify which one is poor and which one is rich. In Zaitchev's rule, the general idea is the poor get poorer, that is the one that has the least hydrogens, the carbon that has the least hydrogens attached to it is the one we're going to remove the hydrogen from. So in this case, the poor one is the carbon on the left hand side. So we are going to produce this product here. Okay, so we're going to make a double bond in the middle here, and this is going to be but2ene. This is the major product. Now remember, because there are two options, so there is this poor option, or the one on the left hand side where there's only two hydrogens attached, or there's the one on the right hand side where there's three hydrogens attached, the rich one. This one happens less often and produces the minor product. So because there were two different options that would produce two distinct products, different products, we use Zaitchev's rule to work out which one is the major product and which one is the minor product. And remember, Zaitchev's rule states the hydrogen atom will be removed from the adjacent carbon with the least hydrogen atoms bonded to it. The poor gets poorer. And that's elimination reactions using Zaitchev's rule. Okay, so let's just look at some reaction schemes. If you want to just pause here, what you can do is have a go and work out, okay, what are the reactants here? What are the reactants or the products? What is the missing reagent, or what is the type of reaction? So fill in the spaces of these reaction schemes and see if you get the same answers as me. So the first one here, we have an alkene, it is propene. We are adding the reagent Br2. Now remember, because we're adding the diatomic halogen, a bromine molecule made of two bromines, what happens is the double bond breaks, and then a bromine is attached to each carbon that was part of the double bond. So we get this molecule here, which is 1,2-dibromopropane, and because we have added something, broken this double bond and added something, this is called an addition reaction. Let's look at reaction 2. Now, because these first two reactions are alkenes, it's highly likely that they are addition reactions, and this is also an addition reaction, but instead of being a diatomic halogen, we have a hydrogen halogen molecule here. We've got hydrogen bromide. So again, we're going to break this double bond. We will add a hydrogen to one side and a bromine to the other. And this, of course, is also an addition reaction. Notice that in this addition reaction, a hydrogen and a bromine, and the previous one, a bromine and a bromine. Okay, so now we have a haloalkane, an alkyl halide, we might say. We are adding the reagent KOH alcohol. So we might remember that when we add KOH, or that is potassium hydroxide or sodium hydroxide, in an alcoholic solution, then it is going to eliminate the functional group, the halogen, and a hydrogen from an adjacent carbon. So here we're going to take away the chlorine and a hydrogen. It doesn't matter which hydrogen because this molecule is symmetrical here. So this is called an elimination reaction, and this is going to produce prop-1ene. Okay, so down here at problem 4, we can see that there are two possible products. So immediately I'm thinking, okay, two possible products at this level with the chemistry, organic chemistry. There are the two types of reactions we're thinking about: addition, when we use Markovnikov's rule, or we have elimination using Zaitchev's rule. Now, because there is no double bond here, but there is an OH, we can see this as an elimination reaction. And, we can see the reagent here is concentrated H2SO4, so it's going to take away a water molecule from this alcohol. So we are looking at the OH here, we're going to remove it, and then a hydrogen from an adjacent carbon. Now, if we remember Zaitchev's rule, we remember that the majority of the time, to make the major product, we are going to remove the hydrogen from the adjacent carbon that has the least hydrogens, the poorest, and that's the one on the right here. And the one on the left is the richest. So this is an elimination reaction. We are going to produce the minor product is going to be when we take the hydrogen away from the richer one, or the carbon with the most hydrogens on the left. And the major product is going to be when we take the hydrogen away from the adjacent carbon that has the most hydrogens attached. This is an elimination reaction as well. Okay, so one last problem here. Oh, okay, we have the answer, but that's fine because we've given the reagent here. We can see that the reagent is hydrogen gas, hydrogen molecule. It's in with a platinum catalyst. So if you've remembered your reagents and how they sort of pair up with their reactions, we know that this is an addition reaction, and we're adding hydrogens after we've broken a double bond. So we have to draw an alkene that would make this, and the only alkene that can make this is propene. Okay, and this is going to be an addition reaction, and that is reaction schemes. Okay, look out for the extra videos I have on reaction schemes. They're going to get progressively harder until we become very confident with them. So before looking at this video, it would be really helpful if you've gone through and remember the reagents that are used to carry out elimination reactions and addition reactions, and also understand about Zaitchev's rule for elimination reactions and Markovnikov's rule for addition reactions. So what we want to do here is look at how we can do a sequence of organic reactions to produce the organic product we want. And in this case, what we have here is we have propane 1-ol, and I want to go and turn it into propane 2-ol. And what I can do is a sequence of elimination and addition reactions that will move where the substituent, the OH, is attached. In the start, the OH is attached to the carbon. So I'm going to add concentrated sulfuric acid. And if we remember that when we add that reagent, what it does is remove the OH and a hydrogen from an adjacent carbon. So it's going to remove these two substituents here. Well, a hydrogen isn't really identified as a substituent, but it's going to remove the hydrogen and the OH group. And it's going to produce this alkene here, prop-1-ene. Now, if I want to remember, I said that I wanted to turn it into prop-2-ene. I'm now going to have to carry out an addition reaction to add the OH back, but I want to add it to the second carbon. Now, we're quite lucky because what happens here is when I add H2O, H+, then the majority of the time the hydrogen will add to the carbon with the most hydrogens already. That's the first carbon here. And the OH group will add to the carbon here with only one hydrogen after the double bond is broken. And that will form propane 2-ol. And the reason it does that, remember, is because this carbon can be said to be rich in hydrogens, and we have the general rule that we remember: the rich get richer. So this is the major product. So I can go through these two reactions, and when I do this, I have changed this molecule from propane 1-ol to propane 2-ol. Now, if I needed propane 2-ol for further organic reactions to make a specific molecule that I wanted, I could source it or make it from this propane 1-ol I originally had. So here's an example of the type of question you might have. Explain how you might convert 2-chlorobutane into 1-chlorobutane. Assume you're able to separate the minor product and the major product. Include a reaction scheme in your answer. So, well, I'm writing a reaction scheme, so let's write down the reagent, 2-chlorobutane. I want to turn it into 1-chlorobutane, so I'm going to have to turn it into an alkene for a start, right? And the alkene must have the double bond on the end in order to add the chlorine to the first carbon. So here, the first reaction is going to have to remove the chlorine and the hydrogen from the carbon off the first carbon. Now notice if I remove the chlorine here, okay, and we're going to do that by adding potassium hydroxide dissolved in alcohol. So I remove the chlorine. The reaction I want to happen is removing the hydrogen from the carbon that is adjacent, that has 3 hydrogens, not the carbon that has 2 hydrogens. So what I'm going to produce here is I need the minor product of this reaction. So here I've produced the but-1-ene, which is important because if I don't have but-1-ene, I can't make 1-chlorobutane because I can't add the chlorine to the first carbon. But remember that this is a minor product. Okay, and we have to assume that if we produce the minor product and the major product, we can separate them apart from each other. Okay, so now what I want to do is add HCl. And again, we have to recognize here that when we add HCl, the majority of the time, when we break the double bond, the hydrogen will go to the carbon with the most hydrogens, and the chlorine will go to the carbon with the least hydrogens, the majority of the time. But we want the chlorine on the first one, so we're going to get the minor product as the one that we want. Now, this is the reaction scheme that we were asked to do. Explain how you might convert. So I need to explain this as well as drawing it. So to a sample 2-chlorobutene, I added potassium hydroxide, alcohol heated. I collected the minor product, and then to the sample of this minor product, I added HCl and heated and collected the minor product again. Now be aware here that when we collect the minor product is always less than 50% of what I started with. So that first amount here, so if I started with 100% of this, I've got less than 50% of this, and then less than 50% of 50% is less than 25%. So actually in the end, I'm going to get not much of what I wanted. And that's one of the problems with very long reaction schemes, is actually the yield or the amount of product produced from what I originally started with can be quite small, especially if I have to go through these reactions where it is the minor product that I want. Okay, and this is the next question I had here. Discuss the expected yield. So as I said here, if we notice that each of these reactions produce less than 50%, then overall we're going to have 50% of 50%, which is less than 25%. Isn't great if I wanted to collect the product. And that's how we might use elimination and addition reactions to move the position of the substituent on an organic molecule. Okay, so let's have a look at some reaction schemes. These ones here involve 2 steps, and they're all starting with either an alcohol or a halogen. So what you need to do here, stop the video, see if you can identify what are the types of reactions, the reagents, the intermediate product, or that's found in the middle of the step, to produce the final product that's shown. Once you've done this and filled in all the spaces, I'll go through the answers. Okay, so the first one here, we can see we started with an alcohol, and then we've produced this alkane. Okay, so how do I do that? I can't substitute an OH, a hydrogen, for an OH, but what I can do is I can have an elimination reaction. I can remove the OH and the hydrogen to produce an alkene. And this is going to be an elimination reaction. And remember, to remove this here, I need concentrated sulfuric acid, concentrated H2SO4. Now here, because I have an alkene, I can turn it into an alkane by adding hydrogen, hydrogen H2 in the presence of either platinum or nickel, and this is an addition reaction. Here I'm using platinum, but you could have nickel down as your catalyst. Okay, the second one, we're starting with an alcohol again, and what we want to produce is an alcohol off a different carbon. So to do that, remember, if you've seen the video that I had on how to use elimination and addition to move the position of the substituent, the first thing we do is we do an elimination. We make this prop-1ene here. To eliminate this again, we're using concentrated sulfuric acid. To make this reaction happen, the minor product will be produced when the hydrogen is bonded, after we break this double bond to the hydrogen that has the least carbons, and the OH will attach to the other carbon, sorry, the carbon that has the least hydrogens. So here, this is going to be an addition reaction. We are going to use water in the presence of dilute acid. We could just write dilute sulfuric acid. That would be an acceptable answer for the reagent. The major product is obviously going to be when we have the OH in the middle, but obviously if we went through this reaction scheme, it is the minor product that we would be wanting to make. Okay, so Problem 17, we can see this is a haloalkane, and again we've shifted position from the haloalkane on the end to in the middle. So the reaction type, the first one is we're going to carry out an elimination reaction here. We have removed the chlorine and a hydrogen from an adjacent carbon. We used potassium hydroxide here. We could have used sodium hydroxide in alcohol, but remember it has to be dissolved in alcohol. We need the brackets here with that saying that. And then we carry out an addition reaction. Now notice that this is the major product. What we've added here is we have added HCl, concentrated HCl. And what happens the majority of the time, because of Markovnikov's rule, the hydrogen will attach to the carbon that has the most hydrogens, and the other group or atom will attach to the other carbon. And this is how we get this product. And these are reaction schemes, problem 15, 16, and 17. Okay, let's look at some substitution reactions. So substitution is a type of reaction that occurs when a functional group is removed and it's replaced by another functional group. It's just like if you had a substitution in a sports team. One person is replaced by another. Now, halogens often are involved in substitution. They're highly reactive atoms, so often we are having the halogen that is being replaced, or the halogen is doing the replacing. So let's look at these 5 different examples of halogen reactions. So the first one here is when we have an alcohol and we're going to replace the alcohol with a chlorine group. Here with the reagents we can use PCl3, PCl5, and SOCl2, that is phosphorus trichloride, phosphorus pentachloride, or thiochloride. And what we're doing here is just all we're interested in, and we're looking at the group that is changing. That's the OH. We're adding a reagent to make the change, and this is this phosphorus pentachloride, and it's taking away, it's removing the OH and replacing it with a chlorine. So we've turned an alcohol into a haloalkane. And the second group of reagents do exactly the same, apart from in this case I could use hydrogen bromide, hydrogen chloride, hydrogen fluoride, and they will replace the OH with the halogen that is present in the hydrogen halide compound. So for example here we could have alcohol, which is ethanol here. We add hydrogen fluoride to it. It is the fluoride that is going to replace the OH. And we would have an extra product left behind here. It would just be water, because the hydrogen and the OH would get together. Okay, so we've turned an alcohol into haloalkane again. So the next one we're looking at here is we have a haloalkane, okay, and we are going to carry out a substitution reaction. We're going to remove the haloalkane and replace it with an OH group. And we'll do that by adding potassium hydroxide or sodium hydroxide, but they are dissolved in an aqueous solution. So what we do here is we put a bracket at the end of the reagent here and write AQ to say it's dissolved in water. So here, notice we have a fluorine attached to the carbon, or the first carbon here. We are replacing this with the OH that comes from the potassium hydroxide in the same position. And in these substitution reactions, the reaction is happening at on the same carbon, the same position every time. Okay, the next part here is we could take a haloalkane, and if we add concentrated ammonia or ammonia dissolved in alcohol, what will happen is we can remove the chlorine and we can replace it with an NH2 group. And what happens is a hydrogen from the NH3 is going to go away with the chlorine, and we'll get hydrochloric acid as well. And so we're replacing again off this first carbon the Cl with NH2. The last one we have here is a substitution reaction. This one is a bit different in that there is no halogen involved, no haloalkane or alcohol. This is just an alkane. What happens here is actually this molecule is really unreactive, but if we put it in sunlight, ultraviolet sunlight will actually break one of these bonds and remove one of the hydrogens, and then the bromine will come in and it will take the position where one of the hydrogens were. It's important to note and remember in this case that the Br2, only one bromine is replacing one hydrogen in this example, and that the other bromine goes away with the hydrogen. Now this is a common reaction. It's used to it's just used when we have to explain how we identify alkenes or unsaturated compounds. This reaction takes place over about 30 minutes in sunlight, and what will happen is that this bromine water that is an orange color will become colorless slowly over 30 minutes. And those are substitution reactions. Hopefully this video has been helpful. Look out for the other videos I have in this level 2 chemistry. Okay, so here we have some reaction schemes, some problems of reaction schemes. We've got 4 different reaction schemes here with just one step in each. I've either put the product or the reactant here. Maybe there's a reagent, maybe there isn't. You have to work out the reaction type, what's missing with the product or the reactants. Just pause the video, see if you can work them out, and I'll go through the answers. Okay, problem 6 here. Compound B turns into this propene here, and we can see that the reagent is potassium hydroxide, which means it's an alcohol. So when we have hydroxide in an alcoholic solution, it is undergoing an elimination reaction, and it's eliminating a haloalkane. So actually I could put in this here, I could choose any haloalkane. So it could be a chlorine, a fluorine, a bromine, or an iodine. You choose. In this case I chose a chlorine. Okay, I've put the chlorine off the second carbon. It could also have been off the first carbon. That would still produce the same product. This is of course an elimination reaction. Okay, so the next one is, we're given the reactant, can we work out the product? So we have this PCl5, and if we remember from our substitution reactions, this is a substitution reaction, and the chlorine from one of the chlorines in the PCl5 is going to replace the OH. So this is a substitution reaction, and the molecule we have here is 2-chloro-2-methyl propane. Okay, problem 8. So we can see here we've produced a haloalkane by adding HF. So there is, I guess, in this case we could do this 2 different ways. You could have started with an alcohol and produced, because the alcohol could have been in the place where the fluorine substituent is, we could have had an OH. But if we'd done that, we wouldn't have got 2 products. Because we have a major and minor product, we know that this must be an addition reaction that has used Markovnikov's rule. So there must have been a double bond in here. So this is an addition reaction. There is a bute-1-ene. And remember, I knew that it was not butane-1-ol, it was bute-1-ene, because it had 2 possible products. Okay, because remember, we could add the fluorine to the first carbon or the second one when we break the double bond. So what is our major product? Well, it's when the hydrogen is added to the carbon that has the most hydrogens already, and the fluorine is added to the other carbon. Let's look at problem number 9. So problem number 9, we have propane here, we're adding Cl2. So this is just straightforward addition here. We break the double bond and we add a chlorine to each carbon where the double bond had been. And here we get 2-dichloropropane. The last one here is an addition reaction again, because we've got the double bond here. We're adding water in the presence of dilute acid. So we're going to add a hydrogen to one side and an OH to the other, and we get butane-2-ol, and that is some reaction schemes with only one step. We've looked at 3 different types of reactions in these reaction schemes that we had to identify: elimination, substitution, addition. Really important you get your head around these types of reactions and the reagents that are used for them to happen. Okay, thanks for listening. Okay, so in this video, we're going to look at adding potassium hydroxide or possibly sodium hydroxide to haloalkanes. So when we do that, there are 2 possible types of reactions that can occur, which would result in at least two different possible products. So the reagent can either be dissolved in water, which is KOH aqueous, or it can be dissolved in alcohol, which is KOH alcohol or ALC. So when KOH is aqueous or dissolved in water, we have a substitution reaction. And what that means is that in this case, the halogen substituent, the Cl, is going to be replaced by an OH or a hydroxy alcohol group. So it's going to change from a haloalkane to an alcohol. However, if we add the potassium hydroxide and it's dissolved in alcohol, or KOH ALC, an elimination reaction occurs. So if we had a haloalkane, we are going to take the chlorine and we're going to remove the hydrogen from the adjacent carbon. And in this case, the adjacent carbon is the second carbon. So we're going to remove that hydrogen, that chlorine, to make a double bond or an alkene. And so we have 2 different types of products. We can either produce an alcohol or we can produce an alkene. The type of question that we have will look like this. Example, 2-fluoropropane is shown on the right. Here it is. It is reacted with potassium hydroxide. When it's reacted with potassium hydroxide, different products can be produced under different conditions. Give an account of the chemical reactions that occur to produce different products when potassium hydroxide is the reagent. Okay, so under different conditions is a phrase that means potassium hydroxide can either be dissolved in water or it can be dissolved in alcohol. Now, I always remember that if I'm using potassium hydroxide in alcohol, it will not produce the alcohol product. So it's going to produce the alkene. And when I have it dissolved in aqueous, then it's going to produce the alcohol. But the big thing I have in my mind is that, okay, it won't produce alcohol if it's dissolved in alcohol. Okay, that's just, and then I just sort of sort it out from there, knowing that it's going to produce an alkene or it's going to produce an alcohol. So I'm going to start off with the first one here. If we have the alcohol, it's not going to produce the alcohol, so it's going to produce the alkene. It's going to be an elimination reaction. I'm going to give the details here. So in this elimination reaction, the fluorine group and the hydrogen of an adjacent attached to an adjacent carbon is removed, producing a double bond. So 2-fluoropropane is symmetric, so it will always be removed from the first carbon, producing the propene molecule. Okay, so we have this reaction scheme here. So I guess if I want to do this fully, I'm going to say what is their conditions, or I'm going to write that it's potassium hydroxide and it's dissolved in alcohol. The type of reaction, I'm going to draw the reaction scheme and I'm going to name the product. So now we're going to talk about the other conditions, or the other way that the reagent can be, and it can be dissolved aqueous. And remember, if it is aqueous, it's going to make the alcohol. So this is going to be a substitution reaction. In this case, the fluorine is going to be replaced by an OH group, and it's going to produce the alcohol propan 2-ol. And this has all the information we need to get a full answer that might get an excellence grade. Hopefully this has been helpful. Okay, so let's look at quiz 3. This is medium difficulty. We have 6 organic molecules that are drawn here that I'd like you to name, and 6 named organic molecules that I'd like you to draw. So just pause the video, write down what you think of the answers, and I'll go through the answers once you start it up again. Okay, so this first molecule here has 4 carbons in the longest chain, There are no other substituents that are going to change its suffix. It's going to be butane. There are two methyl groups, one coming off the second and one coming off the third. So this is 2,3-dimethyl butane. The second molecule we have here, our longest chain, also has 4 carbons, but it does have a group that is going to change its name, and this is the there's a double bond here, so the suffix is going to be ene, so this is going to be butene, but it's going to be but2ene because it comes, the double bond is off the second carbon. But there are also 2 chlorine substituents here, so it's going to be 2,3-dichloro-but2ene. Okay, so the third one here, there are 1, 2, 3, 4, 5 carbons in the longest chain. There is there is a group. There's an OH group and a CH3 substituent. So the OH is going to change its name to anol. There are 5 in the largest chain, so it's going to be pentanol. We need to number where the OH will be. It will be off the 1, 2, 3rd carbon, so it's propan 3-ol, plus a methyl group coming off the second carbon, so it's 2-methyl pentan 3-ol. Okay, so the next molecule, we have 4 carbons in the longest chain. We have a methyl group coming off the second or third carbon, and an amine group, well, this will be the third carbon, and an amine group coming off the second carbon. Because the amine takes priority, the numbering will start from the right here. Because we have an amine group, we are going to have the suffix of anandamine, and we need to put the number it came off, which is the second, so this is going to be butan-2-amine, and a methyl group coming off the third carbon, 3-methyl-butan-2-amine. Next molecule, 1, 2, 3, 4 carbons in a row. It's a butane. The chloro functional group is not going to change the suffix. There are 2 chlorines coming off the second carbon. Because there's 2 of them that are identical, we are going to use the suffix di in front of the chloro, dichloro, and we have to give a number for the position each chlorine is attached. So it's 2,2-dichlorobutane. The next molecule here is the longest chain that has the carboxylic acid functional group, is 4 carbons in a row. So this is going to be butanoic acid, right? Plus, remember, we have a methyl group coming off here, and we have to give it a number. We number with the 1 starting at the carboxylic acid carbon, so 1, 2, 3. So 3-methyl-butanoic acid. Now it's the molecules we need to draw. Okay, so in the first molecule we need to draw, it's got an hexane here, so it's going to have 6 carbons in a row, and it'll have an ethyl group, which is a 2-carbon chain coming off the third carbon, and a methyl group coming off the 4th carbon. And here we go. So the next one, pent-1-ine, it's going to have 5 carbons in a row, but with a ine is a triple bond coming off the first carbon, and then a methyl group coming off the third one. The second one, propan-diol. Okay, so what does the di mean here? It means there are 2 OHs and they're coming off the second and the second carbon. And the only way we can draw that is 3 carbons in a row, an OH attached at the bottom and 1 at the top. The next one, 2-methyl-pentan-3-amine. 3-amine. This is going to be 5 carbons in a row. The amine group is off the third carbon and a methyl group off the second carbon. The next one, 2-bromo, 3-chloro, pentane, 5 carbons in a row, bromine off the second, chlorine off the third. This one's not too hard. Last one, propanoic acid. Okay, 3 carbons with a carboxylic acid on the end, but 2-methyl, methyl group coming off the second carbon. And these are the names and the drawn diagrams for each of these molecules. Hopefully you went well with that. Okay, so let's have a look at these reaction schemes. We've got 4 reaction schemes, 11, 12, 13, and 14. There are, I guess, 1-step reaction schemes and 2-step reaction schemes. Remember, we're going to be thinking about using elimination, addition, substitution reactions here. We have to draw down what we think either reactant or product that's missing might be, what the reagent might be, or the type of reaction that is occurring. So if you want to work that out first, just pause the video, write down the answers to these and then start the video again and you can go over your answers. Okay, so let's look at problem 11 here. Problem 11 here is a double bond. So initially, of course, we're thinking addition. They've got H2 and a nickel catalyst. Of course, this is hydrogenation, or the type of reaction we could be more generic and just say it's an addition reaction. We are going to break the double bond and add a hydrogen to each point where it was broken, and we get propane made here. Okay, problem 12. Again, we have a propane here. This is a double bond. We can see that there are two possible products. So because it's a double bond and we're producing two proper products, we're thinking, okay, this must be Markovnikov's rule in action here. So we must have added a hydrogen attached to a halogen or an H2O. In any case, this is an addition reaction. We can see here that we have added an OH and an H here, so we must have added water in the presence of acid, so we could have written that down as H2O/H+. And when we broke this double bond and we added the H to one side and the OH to the other side, we could either add the OH to the first carbon or the second carbon. The minor product is when we add the OH to the first carbon, and the major product is when we add it to the second carbon, because remember, the majority of the time the hydrogen will add to the carbon that had the most hydrogens attached to it initially. Okay, problem 13. So we have two steps here. So at the end we can see that we have an alcohol produced, and it has this frame of 3 carbons in a row with a methyl group coming off the middle, so that's going to stay consistent. We can see the reagent we added to get to here was potassium hydroxide aqueous, and remember, when we have potassium hydroxide in aqueous solution, it's producing an alcohol. So and that's correct, but the way that it produced the alcohol was it did a substitution reaction, so it must have started from a haloalkane. Now let's look a bit further higher in this scheme where we can see that they had added hydrogen bromide. So the haloalkane that it must have been a haloalkane with a bromine attached, and because it was substituent, the bromine would have been attached where the OH is attached. So this is a substitution reaction, and this is the molecule it must be. The exact same molecule, but with the bromine in the place of the OH. Now, because the bromine is here in this intermediate organic molecule, the compound B, then when we added hydrogen bromide, it was most likely added, this reaction occurred because there isn't a major or minor product here. So if we'd added hydrogen bromide and there had been a major or minor product, then what we would have known is that it would have been a double bond. But because there's only one product shown here, I'm just going to assume that this was a substitution reaction. And actually, the reagent that the organic molecule they started with here is going to be the same molecule we made in the end. Okay, the bromine. 1-bromo 2-methyl propane, and this is a substitution reaction as well. You could have put down an alkene here, but if you had, remember, you would have had two products. So I'm going to go here with this was just the same initial reactant as the final product. Okay, problem 14. Okay, so we've got here this alkene in the middle. Where did it come from? We've got concentrated H2SO4. That means that this has taken away a water an OH and a hydrogen. There's two possible answers to this. It could have been the OH in the middle, or it could have been on the left. You choose which one you wanted. This is an elimination reaction. Heat and catalyst. Okay, yeah, I remember this now. There's no other reaction apart from we're heating it, we're putting the catalyst in. So this is undergo break its double bond and join in repeating units. It's going to undergo polymerization or addition polymerization. And this is the product we're going to have here. And these are the answers. Remember problem 13, instead of putting the halo alkane here, you could have put down an alkene, but just remember that it would have actually formed two products. Thanks for listening. Okay, so in level two types of oxidation reaction we need to be aware of. Alcohols, they can be oxidized, the OH functional group in alcohols can be oxidized to a carboxylic acid functional group, or a COOH functional group. And if we have alkenes, they can be oxidized to diols. Diols is when we have two OH functional groups attached to one molecule. Let's have a look at these examples here. So the first one I have here is propan-1-ol. So we can see that from the OH functional group attached to the first carbon, this is an alcohol. If we add the reagent permanganate and it's acidified, so MnO4- H+ means it's acidified. Sometimes this is written as KMnO4 /H+. So what this will do is the permanganate actually gets reduced, but we don't need to worry about this when we're writing organic chemistry reactions. But the carbon that the OH is attached to becomes or gains a double bond oxygen and keeps the OH group, and it forms a carboxylic acid functional group. Now, actually, at this level, we don't need to know this, but there is an intermediate that happens along the way that's called an aldehyde, but this is the end product, carboxylic acid from an alcohol. Now, so we can use this acidified permanganate, I said. Now, if we do use this acidified permanganate is actually a purple color, and as the reaction proceeds, the purple color will become colorless. It produces manganese ion, which is colorless, and you will notice that this reaction will go from purple to colorless when you heat it. Okay, so the next type of oxidation, well, the same type of oxidation reaction but a different reagent, is we can add to an alcohol so these are, just to be clarify here, these are both primary alcohols because the alcohol group is attached to a carbon that is itself only bonded to one other carbon. So if we oxidize a primary alcohol here, what we can use acidified dichromate. Now dichromate is Cr2O72-. H+ means it's acidified, and if we do that, we can again change the alcohol group into a carboxylic acid functional group. But in this case, the reaction has a slightly different observation. It will start as an orange color and it will proceed to green. The dichromate will turn into a chromium ion, Cr3+, and it is a green color. And these will actually be used later to identify the presence of primary alcohols. Now we have another type of oxidation reaction, and that is when alcohols get oxidized. Now when alkenes get oxidized. An alkene is carbons with a double bond, okay, between them. And when we add permanganate, and now it doesn't have to be acidified. Sometimes you'll see in questions they write down that it's acidified. It doesn't have to be. We're just adding MnO4-, and what happens is the double bond breaks and we add an alcohol group to the carbon where the double bond broke an alcohol group to each of the carbons, so we produce what's called a diol. Okay, so we change from an alkene to a diol. This is another type of reaction that can be used to identify this species, because if you add permanganate to an alkene, actually this turns into manganese dioxide, which means that this molecule will go from being purple to being brown. And these are the types of oxidation reactions we need to know for organic chemistry. Right, let's see if we can complete these three different reaction schemes using the knowledge that we've learned about oxidation reactions, but also previous knowledge we've learned about addition, elimination and substitution reactions. So we've got problem 21, 22 and 23, and remember, if you're solving these reaction schemes, what you want to do is draw the missing organic molecules or the reaction type or the reagent. So just pause the video, see if you can fill this out, and then I'll go through the answers with you. Okay, so let's look at problem 21. So in problem 21, we can see that we have produced a minor alcohol here, and it's been produced well, we can either go down or upways here. We can see it's been produced by H2O/H+. So obviously that's a reagent we use. We add to an alkene to produce an addition reaction. So this is the minor product that's produced from that addition reaction. So let's identify what the reactant must be. It must have had the double bond coming between the first and the second carbon. And because we see this is an addition reaction, we're going to write that down. It's addition. Now we know that this was an addition reaction. Therefore, the next one we can do is we can see this is an alcohol and it has a reagent of acidified dichromate added to it. And we remember that acidified dichromate reagent is used to oxidize alcohols. And because this is a primary alcohol, this is going to turn this alcohol functional group into a carboxylic acid functional group. So we're going to get this propanoic acid functional group produced. We can also work out what compound D is if we know if we know that it's the major product compared to the minor product from this addition reaction. We can realize here that the OH group is attached to the second carbon. Hey, just always take care when drawing OH groups for alcohols that you show that the bond from the carbon is attached to the oxygen. Sometimes when this is getting marked, if it's not clear that it's going to the oxygen, if it's going to the hydrogen, or in between the oxygen and the hydrogen, they won't give you the mark for drawing it correctly. So now we know that this is an alkene, and it was produced up here from the reagent sodium hydroxide under alcoholic conditions, or we know that this must have been an elimination reaction, and where a haloalkane has turned into an alkene, and it's a major product. Now, major product means that whatever the haloalkane was, the hydrogen must have been removed from the carbon that had the least hydrogens already. So we must have had the chlorine off the first carbon. This is actually not a major product. This is the only product. So there's a wee mistake here, but that's all right. Let's go through to problem 22. So problem 22 is, here is an alkene, and the reagent is permanganate. Notice that this reagent is not acidified. Now remember, sometimes I said by mistake the examiner, the questioner who writes questions for you, might put /H+, but because we see this is an oxidizing agent and we're adding it to an alkene, we know we're going to produce an oxidation reaction. We're going to undergo that, and we're going to produce a diol. So we produce an OH group coming off each carbon that the double bond was attached to. This is not an addition reaction. I mean, it looks like one, but we call it an oxidation reaction. Let's look at reaction scheme 23. So reaction scheme 23, okay, we'll start with a haloalkane, so let's just follow it all the way down. We're adding sodium hydroxide, alcohol. That means this is going to undergo a... If it's an alcohol, it won't produce an alcohol, so it will produce an alkene. It will be eliminated. It will eliminate the chlorine. Here it is here. And an adjacent hydrogen. So there are two possible reactants. They want the major product drawn down. So the major product is the one where the carbon with the least hydrogens is going to have its hydrogen removed. Remember, that's Zaitchev's rule. So we're going to remove the chlorine and the hydrogen for the major product, but to draw the minor product, then we're going to take away the hydrogen from the one that has the most hydrogens. So we're going to have the double bond on the left hand side here. Here it is. It's an elimination reaction. Then we're going to do another type of reaction. This is using Markovnikov's rule. We see we get two different products, a major and a minor. We are going to add H2O to it under acidic conditions. Remember, that's going to add a hydrogen and an OH. The hydrogen, the majority of the time, will go to the side that has the most hydrogens, the rich side. So this will be the major product, and the minority of the time it will go to the second carbon. So addition reaction, major one is where the hydrogen went to the carbon that had the most hydrogens already. And the minor one is when it goes to the carbon, the hydrogen was attached to this carbon here, the second one that had the least carbons. Now we can further react this because it's a primary alcohol. We have an oxidizing agent here, acidified dichromate. and this is oxidation, and we're going to produce a carboxylic acid, and this is our product. Oh, hopefully you did well with that reaction scheme, and look out for the extra ones that I've got up as videos and practice those. Okay, so let's look at acid-base reactions. Now, acid-base, there are in this introductory organic chemistry course, the two types of acids and bases are, there is a carboxylic acid, that is a weak acid, and there is an amine, and that's a weak base. So they're going to undergo the types of reactions we would expect with weak acids and with weak bases. So the carboxylic acid will dissociate with water or react with water. Okay, it's going to donate its proton to water to produce a hydronium ion, and the weak base will partially dissociate with water to produce the amino ion, or minium ion, sorry. So let's see if we can look at the examples of these. So the first one here is our butanoic acid. Now, to show it partially dissociates, when we write this reaction with water, we have to put a forwards backwards arrow, double arrow. And remember, the hydrogen is going to be donated to the water molecule, so we're going to end up with the carboxylate ion here. That is, the O is going to have a negative charge, the carbon double bond oxygen, O negative charge, and the hydronium ion. That's the major change. With an amine, we have this NH2 functional group here is actually going to accept a proton from water, and it's becomes a positive charge, and it will become an aminium ion. So this would be propan 1 aminium ion. We don't have to remember the name for these ions, and it's going to produce the hydroxide ion as well. So these are the dissociation equations in water. The major thing to remember is the functional group of the carboxylic acid. It loses its hydrogen, it gains a negative charge. The ammonia functional group gains hydrogen and a positive charge and produces an OH minus ion. So carboxylic acids, because they are acids, will react with bases. Okay, so if we react with sodium hydroxide, which is a base, of course, the hydrogen is going to be donated to the OH to produce water, and we're going to produce this organic product, which is this ethanoate ion that we will often just draw with the sodium ion. Now, if they had written this equation just as hydroxide, OH minus, we wouldn't write the Na plus down. The next one we can look at is, well, what if we had an amine and we added hydrochloric acid? Well, of course, the hydrogen is donated to the amine to make the aminium ion, and this would be butane 1 aminium ion, and it would then associate this ion with the chloride ion, and we'd get this molecule on the right. The last type of reaction that's quite important, because it's a reaction that's used to identify carboxylic acids, is if we take a carboxylic acid and add sodium carbonate to it, it's going to produce a carboxylate ion again associated with the sodium and carbon dioxide, and it would also produce water. The carbon dioxide is important because we would observe that as fizzing or bubbles in the solution, and that would be, we know what the molecule is now. We know what the functional group is, a carboxylic acid, because the carboxylic acid is the only organic molecule that we learned this year that is going to react with a carbonate to produce carbon dioxide. So these are the 5 different acid-base reactions we need to be familiar with. Right, so we've got another reaction scheme. These have been getting progressively more complicated, so we need to remember about addition, elimination, substitution, oxidation, and now this one also includes acid-base reactions. So we've got 5 different types of reaction types we have to identify and write down into the reaction type boxes. We have to identify the products that are produced from each step. or the reactants they were produced from, and also the reagent when it is missing. So I want you to pause the video to see if you can write these reaction schemes down and the missing parts, and then check to see whether you got the same answer as me. Okay, let's start with problem 24. So problem 24, let's start at the bottom here. We can see we've got this amine here, and we're going to add HCl to it. So this is an amine, this is a weak base, we're adding a strong acid. This is going to be an acid-base reaction. Now remember, the hydrogen is going to get donated to the NH2. This will become an NH3+, an ion, and we'll just put the chlorine next to it. Oh, well, I didn't put the chlorine, but you could write it's chloride ion, sorry, Cl- next to it. And this is the organic product it's turned into. Now, this amine must have come from somewhere, and here we can see we added a reagent, which is alcoholic ammonia, ammonia dissolved in alcohol, or we could say concentrated ammonia. That reagent is used when we want to substitute a halogen with an amine group. So the compound A would have been exactly the same organic molecule, but we've replaced the NH2 with a halogen. In this case, I'm just going to use a chlorine. So this is the molecule that it could have been produced from. You could have put a bromine or a fluorine here. This is a substitution reaction. Now again, if I want to turn an OH into a chlorine, this is a substitution reaction, and I have quite a few choices here. I can use hydrochloric acid concentrated, I can use PCl5, PCl3, or SOCl2. In this case, I used SOCl2. Just note, if you'd chosen here this to be a fluorine or a bromine, you would have had to use hydrogen fluoride or hydrogen bromide here. Problem 25. Okay, problem 25. Well, let's go down. We've got a carboxylic acid here. It's reacting with a base. So, well, sorry, let's go to the top then. We have this haloalkane. I want to turn it into something that's going to become a carboxylic acid. So actually, I'm going to turn it into a primary alcohol. So this is going to be a substitution reaction. I've added potassium hydroxide in aqueous. Okay, it's in aqueous conditions. That means that it will produce the alcohol, and it will swap out the OH for the Cl. And the reason I chose that is because I knew this had to be a primary alcohol, because that's the only way that I can make this carboxylic acid group. And we see here that we're adding an oxidizing agent to the primary alcohol, so this is an oxidation reaction. Carboxylic acid here, if we add it to a strong base, of course, we're going to lose the hydrogen, the H+, and we're going to make this a butanoate. But this is an acid-base reaction, and we're going to make this butanoate ion. And remember, we can put the Na+ beside this as well. So the next step, the next scheme, sorry, 26. We're going to start with this compound at the top here. This is propene. We are going to add what? Okay, we've got HCl as our reagent. Obviously, this is going to be an addition reaction. There are two products. The major product will be the one where after the double bond is broken, the hydrogen attaches to the carbon with the most hydrogens, and the chlorine will of course attach to the other carbon, the second carbon. So this is the major product, and the minor product will be when the hydrogen attaches to the carbon with the least hydrogens, and the chlorine attaches to the first carbon, and this is the minor product. So now we have this. We see here that the product after the next is the carboxylic acid. So that must have been made from a primary alcohol. So this needs to turn into a primary alcohol. And to do that, we have to have a substitution reaction. And to do that, we are going to use sodium hydroxide. And it's going to be in an aqueous solution, right? So remember that if we have sodium hydroxide in aqueous solution, it makes an alcohol. If we have an alcoholic solution, it makes an alkene. So because this is an alcohol, we turn it into carboxylic acid. We know this is an oxidation reaction. We are going to either add acidified permanganate, or acidified dichromate. In this case, I chose acidified permanganate, MnO4- /H+. This carboxylic acid is going to react with sodium carbonate. It will produce carbon dioxide bubbles, we observed. This is an acid-base reaction, and it's going to produce carboxylate ion, a propanoate ion, plus the sodium that goes with it. And this is the answers to these reaction schemes. Okay, so here's a fourth quiz here on naming organic molecules, simple organic molecules. It's a medium level of difficulty. Don't forget to use the rules on the left and the table on the right to help you remember the functional groups and their suffixes and prefixes, and the table down the bottom to if you need to remember how many carbons there are. Now there are 6 molecules to draw and 6 molecules to name. So if you just pause the video now, and then I'll go over the answers when you restart it. Okay, so let's have a look at the answers. So the first molecule we have here is 2,2-dimethylbutane. Because it's butane, it's going to have 4 carbons in a row, and a methyl group coming off the second group, or 2 methyl groups, because it's dimethyl, both coming off the second carbon. So it will look like this. The second one is cis-butene. So again, because it's bute, it has 4 carbons in a row, but because it has the suffix -ene, it's going to have a double bond. The double bond will come off the second carbon in the chain because it's butene. Cis means the arrangement of the substituents or the atoms coming off the carbons that are part of the double bond. They must either be on the same, both on the top or the bottom, and in this case we can see this is a cis arrangement. So the next one is 3-methylbutane-2-ol. 4 carbons in a row again. Anol means that there must be an OH and it's off the second carbon. And then we have a methyl group, a CH3 group off the third carbon. And here it is. 2,3-dimethylbutane. Again, 4 carbons in a row. Di means there are 2 methyl groups. Methyl group's the CH3 group, so they're coming off the second and the third carbon. So it looks like this. Propan 2,2-diamine. Okay, now remember we put the 2,2 in. We can't just put 2 because it's diamine. There are 2 amine groups. We need to say exactly where each is attached. They're both attached to the second or middle carbon on a propanamine chain, and it's amine, and anamine means that it's got that suffix because it's an amine. 3-bromopropanoic acid. So we'll draw 3 carbons in a row with a propanoic acid functional group on one end, and then we start numbering from the ethanoic acid, sorry, the carboxylic acid functional group, 1, 2, 3, so it's 3-bromopropanoic acid. Okay, so the next part we're going to do is name these 6 molecules. The first molecule, we have 1, 2, 3, 4, 5, pent, 5 carbons in a row. We have a methyl group coming off the second carbon and an ethyl group, that is a CH2, CH3, coming off the third carbon. And remember, we are going to write the ethyl group as the first prefix because it is the E is at the start of the alphabet, is closer to the start of the alphabet than the M. So this is going to be 3-ethyl 2-methyl pentane. The next one here, we have 1, 2, 3 carbons in the longest chain. We have a triple bond, which means it's going to end with ine, Y-N-E. Triple bond is coming off the first carbon, so it's 1 ine. And we have a fluorine group, which is fluoro, coming off the third carbon. Because we can see here that the triple bond has a higher priority than the fluoro functional group, so we're going to start numbering from the left. So here we're going to have 3-fluoro-prop-1-ine. So our next molecule has 1, 2, 3 carbons in a row, but we now have 1, 2, 3 OH hydroxy functional groups. Now, because they are hydroxy functional groups, the suffix is going to change to an ol, but because there are 3 of them, it's going to be triol, and because they come off the first, second, and third carbon, it's going to be propan 1,2,3 triol. The next molecule, 4 carbons in a row, bute. It has amines coming off, so it's going to be butanamine, and it's got a methyl group coming off. 2 amines, so it's going to be butanediamine, and we have to give the numbers, so it's butan 2,3-diamine, but a methyl coming off the 2 as well, so it's 2-methyl butan 2,3-diamine. The next molecule, 1, 2, 3 carbons in a row, we have a chlorine group coming off the second carbon and an iodine group, chlorine atom, and an iodine atom coming off the first carbon. We are going to, when we write it out, make sure that these functional groups are in alphabetical order. The chloro goes before the iodo because C is before I in the alphabet. So we are going to name this 2-chloro, 1-iodo-propane. The last one here, you can see that there's a carbon double bond oxygen with an OH attached. This is a carboxylic acid functional group. There are 4 carbons in the chain, so it's going to be butanoic acid, and there are 2 methyl groups coming off the second and the third carbon, because remember, we start numbering from the carboxylic acid functional group. So we have 2,3-dimethyl butanoic acid. And that is the end of this answers for the naming quiz. Good luck. Often we're going to be given a scenario where we will have unknown samples of organic substances. Now, all of these organic substances that we're going to be given are going to be liquids at room temperature, and they're going to be colorless. So we can't identify whether they are alkenes, alcohols, haloalkanes, alkanes, amines, or carboxylic acids. However, there is a series of tests that we can do to identify what type of functional group they do have. So the tests we're going to look at in the next couple of slides are adding bromine water, adding permanganate solution, adding acidified dichromate, acidified permanganate, water. You can bring haloalkanes close to a charged particle. You can use red litmus for test for amines. You can use blue litmus to test for carboxylic acids, and you can add carbonates to test for carboxylic acids. So let's just go on and have a look at some of these examples. Okay, so the first example that we have here is what's called a permanganate test for an alkene. So if we take a sample of an alkene, and it could be something like cyclohexene or hexene, and we add some purple permanganate solution. Now remember, it doesn't have to be acidified. Sometimes they might have a /H+ to show it's acidified. It won't make a difference. When we add purple permanganate to the alkene and shake it, it goes brown. So it goes from purple to brown. Now, if we see this is the reaction that happens, we have a double bond, it produces a diol, it has undergone an oxidation reaction. And the positive test, remember, for an alkene here is we added permanganate and it changed from purple to brown. So we can also do a test for alkenes. We can do what's called the bromine water test, and we take a sample of it again. We add some bromine water to it, and then we give it a shake. Now, and then if it changes, it goes colorless and within 10 seconds, then we know that we have an alkene. Now, what's happened here is this is an addition reaction. What's happening here is the 2 bromines from the bromine molecule, the double bond breaks, and then they add to the place where the double bond, to the carbons that were part of the double bond. So we get 2 bromines added. Now this has undergone an addition reaction to produce a haloalkane. And the solution for this bromine water test is a positive identification for an alkene as the solution changes from orange to colorless. We can also just do if we do a bromine test with an alkane or any other organic molecule that doesn't have a double bond or a triple bond, then the following will happen. If we add the bromine water to, let's say, a sample of alkane, it's going to stay orange. But if we put it in the presence of ultraviolet light, what the ultraviolet light does is it will actually react with the alkane chain, and it will radicalize one of the hydrogens and remove it, and then that will react with the bromine. So it will take 30 minutes. So it's actually not a definitive test. Any organic molecule is going to do this reaction with bromine water. It takes a long time, over 30 minutes, in the presence of ultraviolet light. Now, this is not a positive test for, it isn't a positive test for alkanes because all organic molecules have alkane molecules. However, we do know that a substitution reaction has happened. Okay, so often what will happen is you will carry out the bromine water test on both an alkane and an unknown alkene, and the one that reacts and changes color from orange to colorless very quickly we know is the alkene, and the other one must be the other molecule, the alkane. So if we want to do a definitive test for a primary alcohol, or if an alcohol functional group is present, what we can do is we can either add acidified dichromate or acidified permanganate. With the acidified dichromate, we'll take a sample of the alcohol, and then what we'll do is we'll add to it a solution of acidified dichromate. Now, sometimes you'll get the solution is already made up, the dichromate acidified. Other times you might add some unacidified potassium dichromate and then some acid as well. But if you don't make it acidified, it's not going to work. So we add the sample to here. It's orange for a start. We place it in a water bath for about 5 minutes. Sometimes it reacts quickly. Sometimes it needs a bit of heat to make the reaction happen. But it will go a green-blue color. It will start becoming more green and then eventually become green. And if you leave it for long enough, it'll go a bluer color. Now, this is because what's happening here is the alcohol group is turning into a carboxylic acid functional group, and at the same time the dichromate molecule is turning into the chromium ion that is a blue-green color. Now, this is an oxidation reaction, and this is a definitive test for alcohol groups. It can be used also for aldehyde functional groups, but at level 2 NCEA chemistry we don't need to know about those. So the solution changes from orange to blue-green. If we could use acidified permanganate, which is another oxidizing agent, it is purple. Its formula is MnO4 minus, and there's a /H+ because it has been acidified. It has acid with it. Now, if the sample, purple acidified permanganate is added to the sample, we can put it in a water bath and heat it for 5 minutes. It will go colorless. This usually goes doesn't need to be heated and will react it itself anyway, but it does go colorless, and that's because the permanganate ion that the manganese ion the permanganate turns into is colorless. So again, what we've done is we've taken a primary alcohol and we've turned it into carboxylic acid. This is also an oxidation reaction, okay, and it is the color change we need to remember here. It's going from purple to colorless. Okay, so let's look at how we might test for amines and carboxylic acids. So essentially we're going to test them in the same way that we would for acids and bases. So amine, we're going to use red litmus paper. The first thing we're going to do, however, is because when we use litmus paper, we have to make sure that the sample has mixed with water to produce the hydroxide ions. So we take the sample and we add it to some water. So we now have an aqueous solution. And then we take that solution and we dip the litmus paper in it, the red litmus paper. And if the red litmus paper goes blue, there we have it, we have an amine. Now the reason that worked is because when we added the water to the amine, what happened is the water donated a proton to become a hydroxide ion, and the hydroxide ion will react with the litmus paper to make it turn blue. Now, amines are weak bases, partially dissociate, produce hydroxide ions. The observation we're looking here is damp litmus paper, damp red litmus paper turns blue. If we want to test for carboxylic acid, we're going to use a blue litmus test. Okay, and we do exactly the same. We take some water, we put our sample in the water, we mix it, we take our blue litmus paper or blue litmus solution, and it will go red if it is an acid. Now again, what's happened here is the carboxylic acid has reacted with water, it's donated its proton and produced the hydronium ion. The hydronium ion causes the blue litmus paper to go pink or red, and remember we need the water for this reaction to happen, so we make sure that there's two ways you can do this. You can mix the sample with the water, or you can make the litmus paper, put it in water, make it damp for a start. So the positive test here is our litmus paper, damp litmus paper, will go from blue to pink. Okay, the other way, so the definitive test, so if we think that we have a carboxylic acid because it went pink, we're going to definitively test this or make sure by taking the sample and adding to that sample some sodium carbonate. Now, the sodium carbonate is going to react with the acid, with the carbonate ions from the sodium carbonate is going to react with the carboxylic acid, and it's going to make carbon dioxide and water. Okay, so that's what it's going to produce, and we will see the carbon dioxide as bubbles. That's our observations. So carbon dioxide gas, positive observation for this is the solution fizzes or gets bubbles. Okay, so the other test that we might use here is called a physical test that we're going to carry. There are a couple of actual physical tests we might carry out to identify, distinguish between different organic products. The first one is solubility test. So what we do here is we see whether the organic substance will mix with water or not, whether it's miscible in water. That means that when we mix the sample and the water together, it just forms one layer instead of two layers. So what we take is we take a sample of water, so we take some water and we add the sample to it, and then once we have these two in the same test tube, we give it a shake. And if the experiment here, or what's in the test tube, only forms one layer, then it's because this molecule is soluble, and it's because it forms hydrogen bonds with water. So if there's a single layer after the sample has been added, it means that, okay, the sample that we've added must be an alcohol, an amine, or a carboxylic acid that has 4 carbons or less. So it must have an alcohol group, an amine group, or carboxylic acid groups, and it must have less than 4 or less carbons in its chain. Now, what actually happens here is, here's an example of an amine. So the amine will actually, these lone pairs that are found at the top of the nitrogen here will form an attraction with the hydrogen particles. Okay, so another physical property apart from solubility we can use to distinguish organic molecules is their boiling points or the melting points. Often we're going to use boiling points because most of the samples of organic substances we have are going to be liquids. So what does that mean? So boiling points, if we're going to separate two things from their boiling points, we need to know the following. The melting and boiling points of organic molecules in a homogeneous series. This is a series that have the same functional group but increased by 1 carbon atom each time, like methane, ethane, propane, butane, pentane, hexane, that's homogeneous series, or we could do the same for alkenes or alcohols. As they increase the number of carbons, their melting point and their boiling point gets higher. For example, here's a table of the boiling points of the straight chained alcohols: methanol, ethanol, propanol, butanol, pentanol, and hexanol. And notice how as the number of carbon atoms of the alcohols increase, so does the boiling point from 65 degrees Celsius up to 157 degrees Celsius. Now, that occurs because as we increase the number of carbons, we increase the number of hydrogens, and actually the molar mass of the molecule is increasing. If we increase the molar mass of the molecule, they have stronger attractions to each other, and that means more energy is needed to break these attractions, and therefore their melting points and boiling points are higher. So what is the type of experiment we can do to identify these two different types? Well, what we can do is we take a water bath, right, or a container, a beaker full of water, and we put our two samples A and B. Now let's say one sample we know is methanol and the other we know is ethanol, but we don't know which is which. So two different samples of alcohols. Well, if I heat this, and if I start to heat this water, so this is colder water, tap water, as I heat the water up, the sample that boils first is the sample that boils at a lower temperature, and that is the sample that has the weaker attractions and the smaller molar mass, and it will be the smaller molecule. So the smaller molecule will start to bubble or start to boil first. So this test that we used here is the sample that boils first must be the sample with the smallest number of carbon atoms. Now, we can only use this test if both of these molecules that we have to distinguish between are in the same functional group. They're all alkanes, or they're all alkenes, or they're all alcohols. And that is how we could use how we could use this water bath test to determine the boiling points and hence distinguish between two different organic molecules in the same homogeneous series. Okay, so these are hard organic molecules to name and hard organic molecules to draw. So I've got 6 molecules to name and 6 to draw. What I want you to do again, please just pause this video, see if you can write the names to these, and then see if you can draw the names of the ones where you've been, draw the molecules where you've been given the names. Just after that, start it up again and I'll go through the answers. Okay, so this first molecule here has 4 carbons in its longest chain. There are 3 substituents coming off: a fluorine group, a methyl group, and a hydroxy group. The hydroxy group, the alcohol group here, it will change the suffix on the end of the name to -ol, and it's off the first carbon because it has the highest priority. So this is butan-1-ol. So we're going to name this 4-fluoro 2-methyl butan-1-ol. So the next molecule we have here is, we have 1, 2, 3, 4, 5, 6 carbons in the longest chain. That's going to be a hex. We have an amine, a methyl, and a chloro functional group. So a chloro, a methyl, and the amine is going to change the suffix. And so that also, we're going to give the amine the priority to the numbering. So we're going to go 1, 2, 3 and give it a number 3. So this is going to be hexane 3-amine, and it's going to be 5-chloro 4-methyl hexane 3-amine. So the next molecule, we have 1, 2, 3, 4 carbons in the longest chain. We have a carboxylic acid group attached, highest priority group, a bromine atom, and a methyl group attached. So we're going to start numbering from the carboxylic acid end, and the suffix is going to be enoic acid. It's going to be butanoic acid, and we're going to end up with 4-bromo and 3-methyl butanoic acid. So the fourth molecule here, again, there is 1, 2, 3, 4 carbons in a row. We have a carboxylic acid on the end, so it's going to be enoic acid. It's going to be butanoic acid. We have a chlorine and a fluorine coming off the 1-second, and a fluorine coming off the 4th. And remember, we're going to write the chlorine first before the fluoro, sorry, the chloro before the fluoro, because we write our prefixes in alphabetical order. So this is 2-chloro, 4-fluoro butanoic acid. Okay, so the next molecule here, 1, 2, 3, 4. Again, notice the carboxylic acid is on the left-hand side, not the right-hand side. It is still in the main chain of 4, so this is going to be butanoic acid again. We have an OH group. We can't, because we've already used the suffix for the higher priority carboxylic acid. The OH group is now going to be a hydroxy group and a methyl group. And because we number from the carboxylic acid side, the hydroxy is coming off 2 and the methyl off 3. So this is going to be here 2 hydroxy 3 methyl butanoic acid. So the next one we have here is there are just 2 carbons in the chain. This is an carboxylic acid, so it's ethanoic acid, and there is a chlorine atom or a chlorofunctional group coming off the second carbon. Remember, we start numbering from the carboxylic acid side, 1, 2. So this is going to be, we could call it 2-chloroethanoic acid, but we only need to call it just chloroethanoic acid because 2 is the only part of the molecule it can attach to, because the carbon that is part of the carboxylic acid functional group has used up all 4 of its bonds. Therefore, this is called chloroethanoic acid. Okay, so the next thing we need to do is draw this molecule. So we've got 3-amino-butanoic acid. Butanoic acid, remember, but, 4 carbons. We're going to draw 4 carbons in a row with a carboxylic acid functional group on the end, double bond O, and joined also a single bond to an OH group. And then as we number along the carbons, that amine group is going to come off the third one, and it's going to look like this. The next one, 3-hydroxy 2-methyl propanoic acid. Okay, so we've got 3 carbons with a carboxylic acid. Off the third carbon that's furthest away from the carboxylic acid group, we're going to have a hydroxy, which is an OH alcohol group, and off the second we're going to have a methyl group, and it looks like this. The next one, bromobutene 2-ol. Okay, this is actually, I've written down here trans 3-bromobutane 2-ol. You can't get a trans bromobutane 2-ol, so let's just assume that this is a butene 2-ol. And we'll draw it like this. Trans, these 2 functional groups are trans from each other, or you could also say the 2 CH3 groups are across from each other. 3,4-diamino-pentanoic acid. Okay, so 5 carbons in a row because it's pentanoic. It's going to have a carboxylic acid functional group on the end, and 2 amines coming off the 1, 2, 3, and 4th carbon. Next molecule here, 2-amino-bromobutanoic acid, 4 carbons in a row with the OIC acid. Bromo coming off the second one. Remember, we number from the carboxylic, start with 1 on the carboxylic acid function group, 1, 2, and 3 for the amine. Last one, methyl butanoic acid, 4-fluoro 3-hydroxy alcohol group, 2-methyl butanoic acid. So 4 carbons in a row with a carboxylic acid, and then a CH3 group off the second, OH off the third, and a fluorine off the 4th. And there we have it. We have the naming for these more complex or harder molecules. Okay, let's have a look at this reaction scheme. So this reaction scheme, you should have gone through all of the different types of reactions that you might have for level 2 chemistry, or what would be your first chemistry course. Organic chemistry course. Now we've got problems 18, 19, and 20. They either have 2 steps or 3 steps in them. Let's look at 18. Okay, so 18, we're starting with a haloalkane. This is 2-fluoropropane, and we want to turn it to something at the bottom. We're not sure, but we know that after 2 different reactions, we're going to form this chlorine molecule off the first carbon. So if we remember back, what we're doing is we're moving a halogen from the second carbon to the first one. We're going to do an elimination reaction and then an addition reaction to make this happen. And of course, we've got the reaction here as potassium hydroxide in alcohol. It's going to carry out an elimination reaction, and it's going to produce this alkene here. We remove the fluorine and then a hydrogen from an adjacent carbon, and it's always going to produce propene. Okay, so now what we're going to do is when we add a reagent to this, we're going to make a chlorine atom attached to the first carbon here, and a hydrogen attached to the other one. So the reagent must be hydrochloric acid, and this must be an addition reaction. Sorry, the first reaction was elimination. This must be an addition, and it must be, here I've written concentrated hydrochloric acid. Sometimes they let you away with just writing hydrochloric acid. I'd always advise you write concentrated hydrochloric acid, just to be sure that you're going to get the mark here. Now, the minor product, of course, happens using Markovnikov's rule when the hydrogen does not go to the side with the most hydrogens, does not attach to that carbon. So this is the minor product here. When it does attach to the carbon that has the most hydrogens, we are going to get this compound D molecule, and this is the major product. Now, the final product here in this reaction scheme is actually when we separate the minor product and we add concentrated ammonia to it. Remember, we can also write this reagent down as ammonia in alcohol. So this is going to be a substitution reaction, and we are going to replace the chlorine with an NH2, and we're going to end up with this, which is propan 1-amine. Okay, so what about reaction scheme 19? We are starting with an alcohol, propan 1-ol. We're adding concentrated sulfuric acid. If we remember, that removes water from the molecule. It removes an OH from this carbon at the end here, and a hydrogen from an adjacent carbon. This is going to be an elimination reaction, and we are going to form propene. What we're going to do here is we're going to carry out an addition reaction. Apparently we're making the major product here. So what happens is that in a major product, using Markovnikov's rule, the hydrogen attaches to the carbon that has the most hydrogens attached, that's carbon 1, and the OH attaches to the carbon that has the least. This is an addition reaction, and this makes this propan 2-ol. Now remember, again, this is a series of elimination and addition reactions to change the position of the functional group on the actual main chain. Okay, so the last one here, we have an alcohol. Kind of stuck here. We can see down here that we're going to add potassium hydroxide and alcohol, and if we remember that it's when we add potassium hydroxide, we're either carrying out an elimination or a substitution reaction. It's either going to produce an alkene or an alcohol. When we add it in the form of dissolved in alcohol, it doesn't produce alcohol, so in this case it's going to produce an alkene. Okay, so we need something here that we can produce an alkene. It has to be a haloalkane. So compound B has to be a haloalkane. So we know this is going to be an elimination reaction. What is the haloalkane it could be? Well, we can choose whatever one we want. I'm going to choose, I'm going to write the alkene here first. I'm going to choose a haloalkene that has a chlorine attached. We have the most reagents I could remember as the ones. We could use phosphorus pentachloride, phosphorus trichloride, thionyl chloride, or hydrochloric acid as my reagent. I'm going to carry out substitution reaction. I'm going to use PCl3, phosphorus trichloride. Down here for the addition reaction, right, concentrated hydrochloric acid, they want the major product. Of course, the hydrogen goes, we break the double bond, we add the hydrogen to the carbon with the most hydrogens already, and the chlorine's going to go in the middle. And there we go. This is our compound D from this reaction scheme. Okay, I've got one more video on reaction scheme if you want to look it up. If you can do those reaction schemes perfectly, you're well set to do well in your end of topic test. Okay, so here we go. This is reaction scheme number 27. So here we're starting with a haloalkane. This is actually 2-chlorobutane, and we're going to turn it into this carboxylate ion, or butanoate, sodium butanoate. We have to go through a series of steps. So let's see if we can work out the I guess organic molecules along this reaction scheme, and there are types of reactions there are and the reagents we need to add. So just pause the video, see if you can fill in the gaps, and then I'll go through the answers. Okay, so let's start here with this molecule. We're adding sodium hydroxide and alcohol. Now, if we remember, when we're adding a hydroxide and it's dissolved in alcohol, it's not going to make the alcohol, so it's going to make the alkene. And we can see that's happening here because we can see there's two different products, and we can use Zaitchev's rule to work out which one is the major and which one is the minor. So if I take away, and remember this is going to be an elimination reaction, I've done the one at the bottom first, let's go through that one. Because I knew that this was the carboxylate ion, I knew it must have come from the butanoic acid. Okay, because it produced a sodium, it's most probably here going to be sodium hydroxide, and it's an acid-base reaction. I could further go back and say, well, C must be an alcohol because that's the only way I'll get a carboxylic acid. And I can either choose to use acidified dichromate or acidified permanganate to carry out this oxidation reaction. In this case, I wrote down acidified permanganate. Okay, so we'll go back to here. We remember that because this produces two different products here, and we've added this, we're carrying out this elimination reaction, we're going to use Zaitchev's rule. And Zaitchev's rule generally is, we remember, it's the poor get poorer, or the adjacent carbon with the least hydrogens is the one that's going to lose its hydrogen the majority of the time. So the minor product, we are going to take the hydrogen away from the adjacent carbon that has the most, because that's the one that's less likely to happen. And we are going to do the major product is we took the hydrogen away from the one that had the least, Zaitchev's rule, and then we took away the chlorine and we made this double bond. Now this is an elimination reaction. Now I just clicked here on my video, but you might have noticed that compound A was, when it went to compound C, it's an addition reaction. We have added an OH and an H to this molecule. This is actually a minor product. I should have written this down here. And this is the end of our reaction scheme. I hope that all went well. And look out for the next video. Okay, so quiz 6 of this series of videos on organic chemistry. What we're looking to do is, can we draw or name the molecules that are given here? What I would like you to do is just pause the video, see if you can draw these correct molecules, or see if you can name these 6 molecules. Okay, right, let's see how we did. 3-chloro, 2-methyl, butane, 1-amine. Okay, so we've got 4 carbons in a row because it's bute. We've got an amine group coming off the first carbon, and then a methyl off the second, and a chlorine off the third. Amine, methyl, chlorine. Oh, nice and straightforward. 3-ethyl, 2-fluoro, pentan, 1-ol. Okay, enol is an OH group coming off the first. So the first carbon of 5 carbons is going to have an OH, the second is going to have a fluoro, and the third an ethyl group. And remember, an ethyl group is a CH2, then a CH3. And that's our molecule there. Okay, so the next one here, 2-iodo, 2-methyl propanoic acid. So propanoic acid is going to be 3 carbons with a carboxylic acid group off the first carbon. Now it's going to have a methyl group off the second carbon and an iodine group off the third carbon. Here we go. Iodo is the term that we use for an iodine atom attached. Isn't on this table here, but it kind of makes sense when you think that chlorine is chloro, bromine, bromo, fluorine, fluoro, iodine, iodo. Okay, the next one. This is actually spelt wrong. It should say hydroxy ethanoic acid. So if this is 2,2-dichlorohydroxyethanoic acid, the hydroxy is the prefix for alcohol group, an OH group coming off the second carbon, and 2-chlorine functional groups, or 2 chlorine atoms coming off the second one as well. And this is ethanoic acid, so it's 2 carbons long, carboxylic acid off the first carbon, and alcohol and 2 chlorines off the second one. Okay, this fifth one here, we've got butanoic acid. There are 4 carbons in a row. There is 2 amino, so 4 carbons, carboxylic acid off the first, amine off the second, and a methyl group off the second and the third. So here we have it. We have a carboxylic acid. We have an amine coming off the second carbon here. And we have a methyl group coming off the second and the third carbon. Okay, next molecule. Oh, sorry, I've already put this up. 2-hydroxyethanoic acid. So it's an ethanoic acid molecule with a hydroxy group coming off the second carbon. So how do we name these last 6 molecules? Well, the first one, we have 1, 2, 3 carbons in a row with a carboxylic acid on the end. So this is going to be called anoic acid. I also have an alkene. Now there is actually a prefix for an alkene, but I haven't put it on here, but we don't need the prefix. So instead of calling this propanoic acid, we're going to call this propenoic acid, and we're going to put a number in to show where the double bond is. So it's going to be propentanoic acid. Plus we have this fluorine here, so it's going to be 3-fluoropropentanoic acid. Sorry, prop-2-enoic acid. The next one here, we have 1, 2, 3 carbons in a row, carboxylic acid, so it's going to be enoic acid. We have an OH and an amine functional group. It doesn't matter which one of these amine or OH is a priority, because the carboxylic acid has already taken the priority and the suffix. But we know that the OH, the hydroxy, is coming off the second carbon and the amine off the third. So this is going to be 3-amino, 2-hydroxy, propanoic acid. Now remember, we put the amino before the hydroxy because we write the prefixes in alphabetical order. Okay, so the next one, again, we have a carboxylic acid and an alkene, so we're going to call this an enoic acid instead of anoic acid. And we have the double bond coming off the second one again, but it's butanoic acid this time, so it's but-2-enoic acid. Okay, so this fourth molecule here, we've got 1, 2, 3, 4, 5 carbons in a row, a carboxylic acid coming off the end here group. So this is going to be pentanoic acid, and if we count along, 1, 2, 3 from the carboxylic acid end, 2 OH groups coming off the third carbon. So this is going to be 2, 3 dihydroxy pentanoic acid. Okay, so the fifth one here, we have 4 carbons in a row, and we have 3 functional groups. We have an OH, hydroxy functional group, a Br functional group, and NH2 functional group. We have to work out which one has the higher priority here, and it is the alcohol, so it's an ol. So I'm going to start numbering from this side as well, and the overall molecule is going to be butan-1ol, butan-1ol, and we're going to have an amino, and a bromine, a bromo. So it's going to be, because A becomes before B, I'm going to put that amino prefix first, and we're going to have 3-amino, 2-bromo, butan-1ol. Last one here is an alkene in our main functional group. So this is pentene. It's coming off the second carbon. So it's going to be pent-2-ene, and it's also got an amine hydroxy functional group, and of course the amine is going to be written first because it becomes before hydroxy in the alphabet. So we're going to have 3-amino, 2-hydroxy, pent-2-ene. And that is the end of my naming here. So look, these are the hardest molecules you'll ever have to name. They will never get that hard in the test. What you do need to think about is, are you trying to apply the rules? Are you applying them properly? Can you remember the prefixes and the suffixes? You won't be expected to know. So when you go and do the amines and hydroxy, let's say an amine, a hydroxy, and a carboxylic acid, you don't have to know which one has a higher priority out of those two. But you do need to remember, the most important things is remember to put things in alphabetical order, right? Try to give the lowest possible numbering you can, and always remember that carboxylic acids have the highest priority. Okay, good luck with your naming. Hey, thanks for watching this video. Hopefully this has made you more confident with your chemistry. Don't forget to like, subscribe, or leave a comment about anything that you want to with this video or any questions you have. I'll see you later.